So, dense nuclear matter plays, both nuclear physics, dense nuclear in understanding these events. From the beginning, dense nuclear matter equations of state can alter the gravitational wave signal. These equations also dictate whether when the merger happens, whether the core collapses or stays as a neutron star. The details of that collapse help drive the emission. So if you don't collapse into a black hole, you could have a magnetar that's another energy source. So that will change what we see when these objects happen, when these mergers happen. They also dictate what the neutrino emission is like, and neutrino physics and the fate of that core can then alter the yields from the disk winds, the disk that forms around that collapsed core. Nuclear interactions play a key role in determining the yield. So you have this thing where nuclear physics determines the gravitational wave signal. It determines the fate of the merged core. It determines the yields. All of this nuclear physics plays a role in that. And then these yields end up playing a strong role in determining what the emission looks like, the quote kilonova that we observe after the merger happens. So it turns out that because they have such a strong effect on all of these properties from everything from the gravitational wave signal to the X-rays to the kilonova signal, we can use those observations actually to start probing nuclear physics. And so having a good understanding of what's the nuclear physics behind all of this is really critical to understanding these events. In addition to all of that, astrophysicists are also excited about understanding these events because these mergers may play a really critical role in producing most of the R process in the universe. And to tell you how difficult this problem is, or where we're at in this, is that if you looked at the rate that we were producing of neutron star mergers from the first event, from the first LIGO detection, GW 170817, we had a rate that said that given the yield that we predicted from the kilonova and the rate that we were getting from these merger events, it was plausible that neutron star mergers produce the bulk of all the R process in the universe. There are papers arguing that they can't produce all of it, and there's good reasons why you can't produce all of it, and hopefully we'll have some talks on that in this meeting. But the problem that has arisen is that after the 03 science runs from LIGO, the rate for mergers went down by about a factor of 3. And so within the uncertainties, you can still explain all of the bulk of the R process from these mergers, but now it's getting a little bit more difficult, and it means that calculating exactly what the yield is from these events becomes more and more important. So I think as time goes on, this becomes a more and more exciting topic to start to do precision, not our normal order of magnitude estimates that we do in astrophysics. So I think both to understand these events and their emission, but also understand their role in doing our process, these are important events. And it's one of these things where there's a lot of it's like a series of studies that need to be done. We need to do merger calculations. These mergers then produce a compact remnant and a torus of material on top of it. We need to follow that torus and figure out what the ejecta from that torus is. So not only do we have ejecta from the merger itself, but also from this torus that's accreting on a compact object. So we need to understand that those ejecta. And so to get this becomes actually a fairly detailed nuclear physics problem, and we need a lot of detailed nuclear physics knowledge to actually calculate these yields. And it's only after you've done all that that you then get to what's the ejecta properties, what's the ejecta composition, that you can then compare what is happening in this merged event to what we actually see as astronomers. So calculating these light curves, we need the morphology of the ejecta, the velocity distribution, the composition, both as a function of velocity space or angle space, and so to get detailed models, there's a lot of physics that goes into understanding these events. And funnily enough, if you look at the physics that's needed at these different phases from the merger and disk calculations to the ejecta evolution, if you look at it, there's a lot of things like nuclear equation of state, neutrino physics, nuclear cross sections, things like fission recycling. And that's kind of the emphasis of this meeting, is this set of physics that plays a critical role in determining what happens when the merger event occurs, how much material is ejected. It dictates some of the gravitational wave signal. It tells us what the ejecta evolution is. It tells us what the final composition is. And so nuclear physics is really at the heart of these events. And so we thought it was a reasonable focus of a meeting to study this nuclear physics. And so that's the goal of this meeting. And the kind of plan of the meeting is to have 3 hours, Monday through Friday, starting at 3 p.m. Central European Time, 9 a.m. Eastern Daylight Time. And every day have those 3 hours. And at the beginning, starting tomorrow, we will have discussion where, usually we would do this in person. We would have our talks, and then we'd go sit around the lovely ECT STAR Institute, and we'd have discussions on the talks that we had heard. We don't have that because we're virtual. So what we're going to do is starting Tuesday, so starting tomorrow, we'll have a period of time where people can just have discussion questions. And so we'll have about 30 minutes every morning where we can discuss the talks from the day before if you don't get your questions done during the talks themselves. And so we can have any questions you come up because you went away and you said, wait a minute, I wanted to ask this. We'll have time for that in the meeting. Then we'll go through, after each discussion, we'll have then talks that are 20 plus 5 minutes, so they're fairly rapid, and go through and have covered different stages of these exciting merger events. So we're going to start off with, we have 5 sessions that we're not quite true to them, but the basic themes of each day are: Monday will be simulating neutron star mergers. Tuesday will be nuclear experiments for neutron star mergers. Wednesday will be equation state effects on neutron star mergers, and then we'll have more on Thursday on equation state details, and then we'll end on Friday with nucleosynthesis from neutron star mergers. So we have 5 days of talks. Hopefully we'll have a lot of discussion. We're a small enough group that you can raise your hand on Zoom, and we can go through the questions, so it should work relatively well. And I'd like to thank ECT STAR for helping us organize this meeting. They've done an excellent job of getting us going. I think this will be an exciting discussion session, despite the fact that we don't get to do it in person. And I look forward to all of your talks. And I want to thank you for the organizers, and I want to thank the ECT STAR staff for all their excellent work. They've really helped us set this up. And I'm done. Any questions?
All right, thanks so much, Chris, for that kind introduction. So as we get ready to launch our morning session, we're going to have a slightly unusual start for the morning. So Stefan Roswag has kindly offered to give us a bit of an intro into neutron star merger modeling, which we will kick off with next. And we'll interrupt that just briefly as the director from ECT STAR comes to give his introduction as well. So, and Stefan, are you all ready? Are you set?
I'm ready. Yeah, that's fine.
Okay, so why don't we get started with a nice introduction to neutron star merger modeling. Go ahead, Stefan.
Okay, can you see my slides? Does that work?
Yes, that looks great.
Okay. Yes, well, welcome everybody. And I have to say my original plan was to talk about a new numerical tool to simulate neutron star mergers, but Chris has asked to also set the stage a little bit. So I'll try to do both. And maybe let's just start with the very basics. I think all of you are here because you agree that neutron star mergers are really just a wonderful topic because they're related to lots of different and interesting questions, starting from binary evolution over gravitational waves, cosmology, high density matter, gamma ray bursts, and of course, one of the major topics here, heavy element formation and the enrichment of the cosmos with heavy elements and potential observational signatures of this heavy element formation. And all of these ideas were around for quite a while. But then we had this really golden event on August 17, 2017. And all these topics were really actually connected. And I guess all of you agree with me that this is a topic that has an enormous potential. But it's of course also very challenging because there's really a lot of physics involved. And that is probably one of the major challenges and one of the major reasons for such a meeting here also, because we need to all join forces to really solve these big problems. Now, to state the question right now is then, so where are we now a couple of years after this event? And I want to just say a few basics, which are probably very basic for some of you, but maybe not for all of you. And I think today, probably most of you would agree that we have actually a fair chance to learn quite something about nuclear matter properties from gravitational waves, which was, well, a decade ago, maybe a bit of an exotic idea. And this is an example now. So this is a little sketch where there is the sweep of a twice 1.4 solar mass neutron star through the frequency range of potential gravitational wave detectors is sketched. And here is the characteristic strain. And initially, as the stars are several or many stellar radii apart, you can, of course, deal with this in an analytical way by post-Newtonian expansions. But once the stars get closer to each other so that their separation is a few stellar radii, they start realizing that they have a finite size and they start becoming tidally deformed. But maybe I should have said this probably also. So I'm starting here with the frequencies from 10 Hertz to a few kilohertz. And I've also briefly indicated the time that it would take for this binary to spiral in. And if it enters the band at 10 Hertz, then it would take about 17 minutes until the merger. But the tidal effects kick in only very, very late. So maybe it's something like 0.01 seconds or so. And at the moment, the current instruments would not be able to see the merger itself. But after the merger, you have, well, here you can probe, since the neutron stars are cold, you can probe the cold dense matter equation of state. But after the merger, you may still have very large neutron fractions, very low electron fractions here. You may have densities, well, close to the collapse to a black hole that may be close to 10 to the 15 grams per cubic centimeter, and temperatures of the order 60 MeV or so several times 10 to the 11 Kelvin. And of course, this is so far pretty uncharted territory. And that's therefore one of the major reasons why the next generation of gravitational wave detectors hopes to see this kilohertz regime here. And this would then also, say, neutron star mergers really cover really a broad range in temperature and density, which is actually also complementary to what you can do in heavy ion collisions. Now, if you want to talk about neutron star mergers as our process source, I think the first idea has been suggested by Jim Latimer, who I think is also here together with David Schramm in the context of neutron star black hole mergers. And the reason why these could be good R process sources is, of course, looking back, very obvious, because in neutron stars you have lots of neutrons, and the minimal requirement that you would need for an R process is that you want to have a large neutron to seed ratio. And if you then plot just the beta equilibrium electron fraction, say, plot the density here, temperature here, and then neutron stars would have, well, maybe here 10 to the 13, 14, or 15 grams per cubic centimeter, essentially zero temperature, then the electron fraction is below 0.1. So it's really lots and lots of neutrons. And provided that you can really eject something, this is, of course, a promising source. This was then confirmed by our simulations, say in the late 90s. There we found, well, it's about 1% of the solar mass that gets ejected. And if the electron fraction is relatively close to what you have in the initial neutron star, then you get a very robust R process. In particular, you get the platinum peak here at a 195. And also, if you take the mass that you find as ejecta and you take the estimated rate, then you find, well, this could be about the galactic R process content. So it was clear already then, and probably earlier also to Jim already, that neutron star mergers could be really a major source. Now the question is, of course, well, do actually the electron fractions remain very close to where they are initially? And in this audience, it's probably not too surprising that, of course, the electron fraction does make a big difference. So this is just the result from a little experiment where you start with a cloud that you let expand and you run a nuclear network. And you vary just the electron fraction here. And then you see, as long as the electron fraction is well below 0.2 or maybe 0.25, something like that, you produce this lanthanide regime and the third peak. But if you go above an electron fraction of about 0.25, then you produce predominantly lighter R process elements. And so this is something like a rule of thumb, this 0.25. And it's important, of course, for the nucleosynthesis, but it's also important because these elements here are important for the opacity, and therefore this electron fraction has also very strong impact on what the electromagnetic signal would be of such a merger. Now, what has GW 170817 really told us? Well, a couple of very interesting things. And one of the first, at least for me, a surprise, I guess for most of you, was that the transient was, first of all, pretty luminous. And second, it started blue after about a day and then became red after, well, a couple of days. And the interpretation is that this is due to material that has an electron fraction above 0.25, while this is due to material that has an electron fraction well below that. And the interesting bit, of course, is now that the initial neutron star has practically nothing of this 0.25 or above electron fraction. If you calculate this a bit more carefully, then you have really something like a few times 10 to the minus 4 of the solar mass. So it's really, this tells us whatever we have seen here must have been produced in the merger. And this is also supported here actually by the identification of strontium lines, which is also a very light R process element. So it was not necessarily the first thing that was probably to be expected. But the punchline to take home from this is that the event produced actually a broad range of electron fractions. And much of that is not present in the original neutron stars. And that means we have really seen, in a sense, weak interactions in flagranti. And they are really important for the nucleosynthesis and the electromagnetic signal. Now, was it really our process? Well, I think we can be fairly sure. So this is one little experiment. And what this is it's showing, again, a spherical distribution of material, let it expand. And I'm varying the electron fraction and the velocities. And what I am overplotting here is the observed bolometric luminosity. So the stuff that you see here as these gold coins or whatever you want to call them, this is the observed bolometric luminosity. The radioactive heating rates are shown by those lines. And you see, as long as the electron fraction is, say, 0.3 or below, you have pretty good agreement. This is stuff that produces, of course, R process material. And if you take substantially larger electron fraction, then you're dominated by individual isotopes, and you don't have a good fit to what has been observed. So I think we can be fairly sure that this was our process. Now, if you have listened carefully, then maybe you've realized that I've cheated a little bit because I'm comparing luminosities, so energy per time, versus heating rates, which are energy per time and mass. That means there's a mass hidden somewhere. And this is actually also an interesting number, I think. And for this experiment, I've used 1.5% of the solar mass. And that means, of course, if we would have a 100% efficiency of what we have observed, then we would need at least 1.5% of the solar mass being ejected. Now, there has been a lot of modeling of the electromagnetic emission, and all these models, essentially all of these models, came up with substantially larger numbers. Some of them, a typical number, something like 6 or 7% of an ejector mass. And here I have to say, I think we should be a bit careful with the interpretation here, because many of these models make strongly simplifying assumptions. And I think Oleg is giving a talk today later about, well, potential effects from things being not perfectly spherically symmetric. And I think it's really fair to say that we also need to make the step at some point to really multidimensional and really physics-based ejector models, rather than by, well, starting with the most simple thing we can come up with. Okay, now just put these 7% into context. So this is now a slide that is actually from 2017 and actually prior to the detection. And there, the game we wanted to play is just assuming neutron star mergers should produce all of the R process in the galaxy. What are the rates that you would need? And I'm putting here in the rates in, well, my preferred units, which are events per year and galaxy. And there's another axis with units that are preferred in different communities, which is per year and cubic gigaparsec. And what this means is that if you want to produce all of the R process, then you need to be on this line. If you want to produce, say, only the heaviest, say above 130, then you should be lying on this red line. Now the question is, what are the rates? Now we can make various estimates. Well, let's start first with what we see in ejector ranges from hydrodynamic simulations. You see the range here is maybe something like 10 to the minus 4 up to a few times 10 to the minus 2. Then you can try to look up in the literature, what do people typically find for binary population synthesis, which would be this range. Or there's from 2015, someone claiming this is the best rate, a few times 10 to the minus 5 per year in galaxy. And you can also overlay short gamma ray burst estimates for the rate if you assume that they're related to neutron star mergers. And what you find here is, well, if you're somewhere here in this type of sweet spot, then so something typically like 1% of a solar mass ejected and a few times 10 to the minus 5 per year in galaxy, then you should be able to reproduce everything that's in the galaxy. And well, this is, as I said, old stuff, but there's a recent rate correction that also Chris has mentioned that actually also agrees pretty well with this sweet spot here. Now, the punchline of all of this is, of course, with the current numbers, which are, of course, not terribly accurate, but with the current numbers, it would be actually consistent that neutron star mergers are the only source. But I think it's likely that there are other sources, and I have just been guessing. I think Almudena will probably talk about this, and Friedel will certainly talk about this on Friday. So likely there are other sources. So a couple of implications. So the first one is really these amounts that we're talking about. They're really huge, and they are a lot compared to what you typically find for the tidal ejector in a merger. And that means if you have something which is complicated enough, assume you can do full GR, general relativistic hydrodynamics, and you have the right equation of state, but this is still probably not enough to explain what we have been seeing. So we need probably additional ejector channels, neutrino-driven winds or magnetically driven winds. A potentially very important source of a lot of ejector is the torus that you produce in a merger. A large fraction of that could unbind, about 40% or so, due to the magnetorotational instability and also nuclear recombination. But this comes at timescales which are, at least for a simulation, uncomfortably long. So these are timescales of an order second, but the dynamical timescales of such systems are fractions of milliseconds. So this also tells us now we need to deal with additional and pretty complex physics, neutrinos, magnetic fields, maybe more. And we need to go to timescales that are, at least from a computational point of view, uncomfortably long. So this could mean something like maybe 10 to the 7 numerical time steps that could be needed. But I guess Jonah will tell us more about this torus unbinding stuff. Okay, so now where does this leave us in terms of the physics that needs to be modeled? Well, of course, we need to make some assumptions, or ideally should know more about the nuclear matter properties, especially at high densities, but also temperature dependence. And there will be many, many talks at our workshop here on this topic. Then another big open problem is how to computationally treat neutrino transport. I guess Jonah will also talk about that, but also about the physics of neutrinos, neutrino oscillations, and I think Meng Ru will talk about that. Another topic that is potentially very important, but also very likely a big box of worms, are magnetic fields. And the reason is we don't know the initial configuration in a neutron star. And we also cannot reliably predict the evolution of the fields, because the fields usually grow by instabilities. And these instabilities grow faster the smaller they are. And that means your numerical resolution is determining what you can see growing as a field strength. And that means it will be terribly difficult to get a physically converged numerical result here for the magnetic fields. Another physics ingredient that, of course, needs to be thought about, maybe not in the context of this workshop here, is, but of course, well, is general relativity good enough, or maybe even approximations to general relativity good enough? Or do we have to go to alternative theories? But that is something which maybe we can leave out here at this workshop. Now, if you go even a step further back, so if we are wondering about the connection between, well, the two things that we could observe, gravitational waves on the one side and this macronova or kilonova emission on the other side, then we also see this huge disparity of scales. So here we have things happening on tens of kilometers within milliseconds. And here we have things happening on 10 to the 10 kilometers and maybe at a week or even after a week. And one of the big questions is then also, well, what is actually happening in between here? And there's a lot of physics involved, but most of this is in today's models actually not really modeled, or maybe in a very simple way. And what you have to do, at least in principle, would be, well, you have to do your merger as good as you potentially can. Then this would give you the ejector with masses, velocities, electron fractions, if you've done your neutrino transport right. Then you can do your R-process calculations. Once you have them, you can really follow the dynamical evolution of your radioactively powered expanding cloud. And then at some stage, you have to do the radiative transfer on this cloud. And then only then you can compare with the electromagnetic signal that you would get. So, so that was kind of like all the physical, well, the challenges in terms of the involved physics, but also the challenges of the involved scales. And of course, well, if you want to do a computational modeling, you have to deal with all of these things. And I just want to now take again a step back, because I now want to come to a new way to model things. And this is now again a summary slide of what we have learned from the first detection event. And we got delivered essentially everything we could potentially have asked for. We got gravitational waves, we got a gamma ray burst. One could start doing cosmology with the event. One could measure that gravitational waves propagate essentially at the speed of light. And it has clarified that neutron star mergers are a very important source of our process. And all of these reasons, this event was elected as the Science Magazine Breakthrough of the Year 2017. And I think it's worth stressing once more that this is really coming from the combined information from the gravitational waves and the electromagnetic waves. Now, if you are really interested in modeling this, then you may have to be aware of that this may require slightly different methods, because the gravitational waves, they are determined by the bulk motion of the material that is happening in the merger. So if you get this right, you may be very good with the gravitational waves. The electromagnetic waves, in contrast, they are entirely produced by a very small fraction of your binary system. So this is just about 1% of the binary system that we're talking about. And it's actually not entirely trivial to know really the physical properties of this only 1% of the system that you're modeling. So you may need different methods, and that is part of the motivation behind our new development here. And that thing is, the major difference is this is a numerical relativity code, but it's a Lagrangian one, so not Eulerian hydrodynamics as is, I think, all of the existing numerical relativity codes. And it's called Sphinx for smooth particle hydrodynamics in curved spacetime. And then there is this addition here, BSSN, which stands for the way in which we are solving the spacetime. And this is due to Baumgartner, Shapiro, Shibata, and Nakamura. And this is actually very fresh. So the paper has just come out in June this year. I will not go very much into details, but I'll try to briefly explain how we do the hydrodynamics with these particles. I will briefly explain how we evolve the space-time, and then I just mention how we are doing the coupling between the two, which we have to do, of course. And if you're interested in the details, please have a look at the paper. I cannot go through them here, of course, but I try to convince you by some very challenging tests that this thing is working very well. Now, the first question that you may be wondering about is, well, why do we want a new numerical relativity code? And one of the reasons in this context here is that Eulerian numerical relativity codes have trouble or are struggling a bit with resolving the ejecta. And there are different problems. One of them is you usually cannot treat vacuum. So if you look at a neutron star, then it should be embedded in vacuum in reality, but you cannot do this numerically. And you have to treat this kind of vacuum as something like an atmosphere, which is some background material for which you have to make sure that it doesn't disturb what you really want to find out about. And of course, that asks then that you really identify which part is vacuum, which part is really physical ejecta. Also, the physical ejecta, they have to escape against this vacuum. And it has to be therefore, well, low enough in density to not hinder the ejecta from escaping. And of course, this transition region between the high density neutron star and this kind of vacuum is just a numerical challenge where usually the methods are struggling. So far so good, but then there's another problem which I think is not often appreciated enough, and that is that of course any astrophysical hydrodynamics code needs to be good at doing shocks, but also advection is a very important property, and that just means if you have a bulk transport of something, that should only change for physical reasons. And this is now, just to illustrate this, this is a little example. So this is just a star that has been prepared in hydrostatic equilibrium, and it's not doing anything. It's just moving in a constant velocity across the computational mesh. And you see it has slightly deformed here, and it has produced those plumes here. And this is just due to advection error. And of course, you can cure this by resolution. But in reality, you normally do not always have the resolution that you would like to have. And the punch, and say especially for the ejecta, these effects can become large because the ejecta are fast and the grids are becoming coarser, and the effects depend on how rapidly you move with respect to the grid. Now, for all of these reasons, it may be interesting to have an alternative method that maybe is struggling less with the ejecta and therefore maybe knows more about the properties of the ejecta. So, and this is, well, here my partner in crime is Peter Diener from Louisiana State University. And we have started this project together. And what we're doing is we're solving the space-time also on a mesh. And we have started with a well-established method that is known to work, this BSSN method, or sometimes also called BSSN-OK. But we want to model the fluid with freely moving particles so that we have zero restriction as far as the particles are concerned. And then, of course, we have to couple the two things. And we're doing this it's kind of a particle mesh method where the fluid is on the particles and the space-time is on the mesh. Now just start with the fluids. Some of you, I know, at least Chris, know a lot about smooth particle hydrodynamics. So this is a way to model a fluid with particles. And in a Newtonian way, you can derive this from a Lagrangian, and you can do this in GR as well. So you just start out, you need the energy momentum tensor and the four velocities and the metric. And then you can do, in a sense, classical mechanics. And this is very much like what we're doing. So we take the canonical momentum per baryon and use this as a numerical variable. And we use the canonical energy per baryon, which is our energy variable. And if you do this, the set of equations that you find looks actually very similar to the Newtonian ones. So you have, so this is the momentum equation. You have a first part which models the pressure gradients, and you have a second part which is coming from gravity. So this is the part that needs the derivatives of the space-time here. And then you have relatively similar terms for the energy. And here you have the time derivative of the space-time here. And so overall, you could say the look and feel of this method is very much like Newtonian SPH, but of course it isn't Newtonian SPH. And the variables that you're evolving are not the variables that you're really interested in. And that means you have to find really the physical variables from the numerical variables several times per time step. But this is very similar to what our colleagues in Eulerian hydrodynamics have to do as well. And so we're also using very similar methods to actually do this. Now for space-time, I can't go much into details here, but we are doing it pretty much exactly like it's done in other numerical relativity approaches. So one uses a so-called 3+1 split, which means one slices the space-time into space-like hypersurfaces and evolves them forward in time. Then you have quantities that are gauge quantities that you can choose. You have a lapse function, you have a shift, and then you have your spatial metric. And the evolution equations are actually, in some sense, similar to what you have to do, for example, in magnetohydrodynamics, because you have evolution equations and constraint equations. Like in MHD, you want to have the diff be constraint conserved. So it's pretty challenging, but it's known how to do. So just to give you a flavor how these things look explicitly. So these are really lengthy expressions. But as I said, it's known how to do it. And we're doing this very similar to what our colleagues are doing in Eulerian hydrodynamics. Now for the coupling between the two, you need, well, the mesh needs the energy momentum tensor, which is known on the particles. And the particles, as I just have shown in the equations, they need the derivatives of the metric because that tells them how they have to move. And that means we have to do, similar to other particle mesh methods, maybe in plasma physics, you have a step where you have to map the particles to the mesh, and you have another step where you have to map the mesh to the particles. But the devil is, of course, in the details, but I can't go into these details here. So now let's assume this is all working. Now we have to do some tests. And the first thing that you would do with a new code, well, the easiest thing would be a shock tube. That you say you start from something which has high density, high pressure on one side, low density, low pressure on the other side. You take out a wall, and then you have a shock moving to the right-hand side. And this shock has a known solution. And this solution is shown here in red. So this is our density variable. This is the velocity, internal energy, and the pressure. And you see our three-dimensional particle numerical solution here in blue agrees very, very nicely with the exact solution. So I would say it's fair to say, well, this box is ticked, so we can do shocks. We have done lots of other tests, maybe one of the more challenging ones here. This is now a neutron star that has been prepared as a Tolman-Oppenheimer-Volkoff solution. And now we are evolving both the hydrodynamics and the space-time together. And we set the star in oscillation and then measure the oscillation frequencies. And this is what we can compare against what our colleagues have done with Eulerian methods. And we find a very nice agreement. So the frequencies that we found agree to better than 1% with what the colleagues have found with their Eulerian methods. And maybe one of the big advantages of our method is that we really have vacuum. So this is now a star that we have really dynamically evolved. So just let the star do whatever the star wants to do. And then wait something like 10 milliseconds, which is already a fairly long time for such a simulation. And in that time, the star had time to oscillate 14 times. But you see, even after that time, the surface is perfectly nice and well behaved. The star red here is sitting pretty much exactly on the initial solution that we had. And in particular, we don't have to do anything special about the surface. So really, our vacuum is really vacuum. And I think this is very good news for this type of method. Now, maybe one last test, and this is a very challenging one. And this is now the evolution of an unstable neutron star, where we say, well, we changed the density, and then at some point, well, this is here the stable branch, and then at some point you have the maximum thing that is stable, and then you can still prepare stars on the unstable branch, and the question is just what happens to them. And this is a test that has been done also in Eulerian hydrodynamics, for example, by Benuzzi and Hilditch in 2010, but also by Biotti a few years earlier. And the answer is the outcome is very sensitive to what you do to the star. So if you just let it evolve, what these guys found is just the truncation error alone leads to very violent oscillations. This is what you see here. So this is their result from Biotti with the central density. But if you give the star a small inward velocity perturbation, then it does something very different. Then it collapses to a black hole. And you see it's a very tiny, the one thing is truncation error, and the other one is a tiny velocity perturbation. That's a pretty delicate test. And we wanted to know, can we do this? And yes, I think we can. So this is the way where we just evolve things. And here you see the star, how it is starting to pulsate. And it's actually very violent. So these outer layers, they get 60% of the speed of light as a velocity. And if you look at the density, it looks very, very similar to what has been found by our colleagues in Eulerian numerical relativity. And now let's do the last thing. Now let's just change the perturbation. It's exactly the same star. We just add a tiny little bit of an inward velocity. And I'm plotting here the particles so that you can see what's happening on the particle level. And you see the star starts collapsing. The black hole starts forming until the star has been eaten up. And also this is in beautiful agreement with what the colleagues in Eulerian hydrodynamics have found. So, and with this, I would like to come to my summary and just say the obvious things. It's a very exciting subject. It contains a lot of physics, and actually also it's related to many exciting astrophysical questions. One of the things we have now learned for sure is that they are a good nucleosynthesis site. And one of the surprises, I would say, was that a lot of material was ejected. There are some caveats, but it was a lot of matter, I would say. And likely the dynamic ejecta are not enough. And that means we have to really take care of complex physics and long, at least for numerical or dynamical timescale of the system, long timescales. And in particular, neutrino transport, I think, is of paramount importance to get the nucleosynthesis right and the electromagnetic signal. And then, needless to say, the numerical modeling is challenging. And one really has to see which approximations one can do. It has to compare them, how good they are with respect to each other. But I think it's also important to not just have a monoculture of numerical methods, but that we also have different methods and compare the different methods against each other so that we can really clearly separate the physics from the numerical artifacts. And with that, I'm done. Thank you.
Okay, thank you very much, Stefan. That was a really interesting talk to get us started. We have already a couple of questions in the chat. So the first hand I saw was Grant Matthews. Grant, you want to unmute yourself and ask your question?
Well, I just had a simple question. In the SPH, there were a couple of problems when people worked on this in the past, and it was dealing with the time dilation and Lorentz contraction going on for the particles. There's also the problem when you're going to run this is that you have a broad range of mass scales. I just wonder how you approach those two problems.
Sorry, I had a problem in acoustically hearing the first part of it. The second one was about the range of mass scales, and the first question was what exactly?
Oh, sorry. The first one was about, I remember years ago when people talked about relativistic SPH, there was a problem with dealing with the fact that you're on a different timeline and you have the smoothing length, you have to properly Lorentz contract it and so forth.
I-
Presumably, there's a way to handle that. I just wonder how you solve that
Yeah.
problem.
I think it's actually not a problem. So we were initially worried about that in the first place as well, but we are doing this actually very similar to Eulerian hydrodynamics. We have a local rest frame of the particles, and we have a computing frame that we choose beforehand, mainly by our labs and shift. And then we have to transform between the two, but I don't think there's any problem related to that. The second problem is the length, I guess the mass scales. And of course, one of the things that, well, we need, of course, also a lot of resolution. So that's the, well, we share this with any other method that tries to model this. And what we are trying to do here is we try to keep all of our SPH particles carrying their own baryon mass, so that we have exact conservation of baryon mass. And apart from that, the rest is what we need to kind of kill with resolution. But since the question was also asking a bit about the SPH part, there's of course, it's of, well, to say it provocatively, it's not your parents' SPH. I think this is an SPH version that has lots of very new elements, including new kernels, doing some very nice things about dissipation, which are actually borrowed from Eulerian methods. And it's still called SPH, but it's very different from the SPH that was around maybe 20 years ago or so.
Hey, thanks, Grant. The next hand I saw up was Chris. Go ahead, Chris.
So Stefan, I agree with you. I think that having multiple methods to try to, see what the uncertainties are in the numerics really make a difference in these studies. And I have a question for you. So in the past, there was a difference between what the SPH calculations were getting and the grid-based codes. And there was arguments on what was missing in the two different calculations. With these new codes, have you done a merger event and compared your ejecta masses for the dynamical ejecta? Are we getting any convergence there, or is it still fairly different in what people are predicting for mass ejectas?
So yeah, that's a very good point, of course. But the first comment I have to make there is, of course, you've seen our paper just came out in June. So now we only have July. So, and we have actually started with empty editors. We have really started from complete scratch writing that thing. And there are many things that we still have to do. And we started with the kind of like relatively well-controlled numerical relativity tests, and we get excellent agreement with our colleagues. And right at the moment, we are working on the adaptive mesh implementation that we would need also for the space-time here to get the full merger. And we don't have yet fully converged merger results, but we had looked at, since you were asking about convergence, we were actually looking in terms of our oscillating neutron stars and so on. We were doing some convergence tests, and it converged at the expected order of an order of 2 overall. So I think it's all very well under control, but still at the moment there's not much microphysics in this version yet. And the adaptive mesh stuff is nearly working, but not yet fully. So there will be stuff coming soon. And the first look, but these are at the moment just polytropic test cases, but there the ejecta masses I see, the first ones, they look similar to what we see with the Eulerian methods as well. But this will be, of course, something that we want to have a careful look at in the future, but we haven't done it yet.
Okay, I think we have time for one more quick question. Jonah, you can go ahead and unmute yourself.
Thanks for the awesome talk, Stefan. This is really cool. I'm really excited to see this method. I noticed you had a comment on the slide where you talk about the collapse of an unstable neutron star. You mentioned that you remove particles in regions where the lapse has started to collapse.
Mhm.
Is this kind of generic to the method? And what does that mean for example, like the baryonic mass or the gravitational mass of the black hole remnant that forms?
That's a very good question. Say in our initial implementation here, we don't have an apparent horizon finder, which tells us where the apparent horizon of the forming black hole would be. So what we are doing here is we let things go, which actually works without crashing. And just once we think we are deeply inside of the forming event horizon, then we start removing particles because they don't give us any information anymore. But we have in a post-processing step tested this. So we have fed in our results into the apparent event horizon finder of the Einstein toolkit. And we found that what we are doing is perfectly safe. So the event horizon is really far outside of that. And also there, the results agree pretty well with what we see in the literature. So this is a first step, which is a bit pragmatic, that we just look at the lapse. And if the lapse drops dramatically at some point, we just say, well, that's fair enough. This cannot avoid black hole formation anymore, and then we get rid of them. But it has been tested and it works. But in the future, we may also go for an apparent event horizon finder just to, well, to answer the questions of people that ask about it. But I think it's fair. It was an extremely low lapse value that we used. I think it was 0.03 or so. So I think it's perfectly safe to do so, but we'll also improve this in the future.
Cool, thanks.
Okay, thanks so much, Stefan, for that wonderful talk to get us started this morning. So for the rest of, or this afternoon, if you are in Europe, sorry. So for the rest of the talks today, we will have 25-minute slots. So I'll give you a warning at 18 minutes and then, except we will not start yet, Almudena, because we have our ECT STAR director here to offer us a welcome. So thank you so much for being coming today, and we look forward to your words of welcome.
You make it sound like I'm like Santa who suddenly appears in front of the door. But so I just have a few things to say. I hope you can see the screen I'm sharing.
Yes, we can see it.
Yeah, great. Okay, thanks a lot. So I'm Gert Aartsendiet. I'm director at ECT STAR since the start of this year. And I know many of you are familiar with ECT STAR, but for those who are not, I just want to give a brief overview. So ECT STAR was founded in 1993, so it's been around for a long time now. And it's a community-driven center for theoretical nuclear physics. And so this is the mission, is to indeed do research in theoretical nuclear physics, promote contacts between theory and experiment, and also to related areas of research, and also contribute to the training of young researchers. And there are two programs that cover this annually. Here are the activities. So the poster is a bit small, but you can see it on the ECT STAR website. So your workshop is somewhere here. All activities are online. Actually, I should update this. They will be online until the end of September. And we're hoping that then at the end of September, we can start meetings in a hybrid mode, meaning there's limited participation face-to-face, and the additional participation is via Zoom, like now. So that will be quite exciting because it's been a long time since we obviously had face-to-face meetings at ECT STAR. Concerning the training program, there are two activities. So the doctoral training program is running now. Currently, it's in the third week. And it's combining high energy nuclear physics with quantum technology. So it's quite an interesting school. And then there is also the talent school, which will start very soon. And that's on machine learning applied to nuclear physics, both experiment and theory. So that's interesting as well. And finally, of course, there's also a visitor program. Currently, the visitor program is dormant because the occupation of the Villa Timbosi is very low. But once we get back to normal business, then please come and visit us, even if there's no workshop going on that you want to attend. We have a Twitter account. We only, we're very late in this. We only joined Twitter in April. So please follow us on Twitter to get updates about the activities. Related areas is very broad. So some of you may know astrophysics, cosmology, particle physics, quantum field theory, but also ultra-cold atomic gases, quantum technology, quantum computing, machine learning. And this I want to emphasize because currently there's a lot of attention and also a lot of funding for quantum technology and machine learning. And there are many interesting relations to nuclear physics, for instance, the quantum many-body problem or data analysis. So there are lots of interesting opportunities here to join in this activity as well. So that's something to keep on your radar. The scientific board is given here, at least the status of the board 1 month ago. It's a collection of researchers from all around, and actually they are suggested by the so-called ECT Star Associates. And the associates are basically participants to workshops and schools. Like you are now in this workshop, so you become an associate for 3 years. And so there is room then to suggest board members. There is a change of board members frequently because board members serve for 3 years. And so this list will be updated soon. And some new board members are in this meeting present, I think. A few words about funding then. So funding comes from various resources. It's the Bruno Kessler Foundation, which is based in Trento, provides the local support. Then there is institutional support from the national funding agencies. And there's also Horizon 2020 or EU funding. And this is interesting because ECT Star is actually recognized as a transnational access facility. All the other transnational access facilities are labs, experimental labs. So ECT Star is the only theoretical lab, so to speak. So we quite a special status in that. And here are some logos of the funding agencies. So these are the national funding agencies from various countries. And then there is the EU funding and some more additional funding. This one I skip. So that's it. For those of you who haven't visited ECT Star, this is the Villa Tembosi, where the coffee breaks and the lunch breaks take place down here on the plaza. And once we get back to in-person meetings, of course, I'm looking forward to seeing you all a little bit better than on the Zoom screen. Okay, that's what I wanted to say. Thank you.
Okay, fantastic. Thank you very much. I also very much look forward to returning to Trento.
Exactly, great. Thank you. Yeah.
Okay, so why don't we continue with the scientific program? Our next speaker is Almudena Arcones. Almudena, hello, how are you?
Hi, thank you. Good.
Great, and I will give you play a tone at 18 minutes and then take questions. And of course, to the audience, if you have questions during the talk, just please type them in the chat. Otherwise, hold them to the end and raise your hand at the end of the talk. Okay, thanks. Take it away, Almudena.
Thank you, Rebecca. Thank you very much for giving me the opportunity to talk. I would be happier if I would see all of you. Seeing the list of participants, I must say I miss you a lot, and I hope we can meet again soon and keep discussing what is really something that we need to produce new results more than future events. I think we need also more in-person discussions. So I will talk about the R process, of course, and I will talk about connecting simulations to observations. So here are simulations of core collapse supernova, magnetorotational driven supernova, and neutron star mergers. So I will mention also this kind of supernova explosion, as Stefan already said. Okay, so we are in a very exciting moment. We have heard already from the introductions of the two organizers. We are in a multi-messenger era, so we can do simulations of core collapse supernova and neutron star mergers. This is what we do also in Darmstadt. Here we include latest developments in microphysics in terms of equation of state and neutrino matter interactions. And then we can compare our simulations to observations to electromagnetic signals of supernova or kilonova, also to gravitational wave signal and neutrinos. In Darmstadt, we are especially interested on following the matter that is ejected in these events through tracer particles and calculate the nucleosynthesis. And then we compare to observations of the older stars, to galactic chemical evolution, and also to the kilonova. So let me start saying what we can learn from abundance observation from a star. So we can do two things. We can look at the evolution with time of abundance, or we can look at patterns and ratios. I would shortly address these two ways of using abundances to constrain our astrophysical simulations and to learn about the astrophysical conditions. So let me start with galactic chemical evolution and show this figure of the paper of also one of the organizers, Benoit. So I feel here we are in a big family. Here you see the evolution with metallicity of europium over iron, and you see that it's more or less flat, and then it goes down. There is a lot of scatter here. This tells us that it's a rare event, so it does not occur in every core collapse supernova, and it goes down because there is iron coming from type 1a supernova. So we can try to reproduce this trend of going flat and then moving down towards the solar value, which you see here. This trend here is with time, so flat and then going down. So in order to get this europium over iron ratio with this bracket notation of the astronomers, we can look at the production rate of the different elements. So iron is produced mainly in core collapse supernova at the beginning, then type 1a is coming to the game. So in order to get this trend, we need the europium production rate that it's here. Mergers produce the dash line. So if we only take into account mergers, we are going to see something going flat towards solar, and this is not what we see from observation. So there is something missing. So if we take what is missing between this dash line and the solid line, we have this residual europium. So we need something putting enough europium early enough, so before the type 1a start putting a lot of iron, and this may point to some rare supernova. We have looked also at abundances not only in our Milky Way. We have also looked at abundances in dwarf galaxies around our Milky Way. This was a work of Moritz Reicha and Camilla Hansen. That they, so Moritz did the PhD in my group, and he prepared the largest set of homogenized abundances in dwarf galaxies. And this is very important to make a strong conclusion, since if you don't use homogenized abundances, the points of abundance can shift quite up and down. So it's important to have everything on the same set. And Marta Molero, who is in Trieste, has used these abundances to do some chemical evolution studies. Okay, so this is a way of using abundances to constrain the site, but this is just more constraining mergers versus supernova. We can also use patterns or ratios between abundances, and this will put stronger constraints on individual sites, on individual astrophysical conditions. And this you see here, this is an old paper that we did, Camilla Hansen, Fernando Montes, and myself. So what we looked was to the abundances of stars that have high enrichment of R process material or low enrichment. So these are called onda stars or limited R stars. And the question is, are those stars here in blue coming from one event, or is the combination of two components of two events, one producing strontium and another producing europium? And then you can add both of them in different ways. So this is what we did. We calculate the abundances, fit into observations, and took a combination of the abundances of these H and L events. So H is the high and L is for low, but you can also see it like a strontium and europium. And I put it even with the colors of the kilonova. And you see here the fits. This is the fits that we did. And we could explain most of the abundances just by a superposition of these two components. And this is good because then we can take the component here, this L component, and use it to constrain the conditions in core collapse supernova. We believe that core collapse supernova may contribute also to these lighter heavy elements. And then if we want to reproduce the ratio of strontium over yttrium or strontium over silver, we have to be in this region. So these are marked with different kind of lines. And you see these are for electron fraction and entropy. So for different conditions, so we can say which conditions reproduce the pattern that we are observing in those stars, this L component or this strontium component. Of course, you cannot use this just straightforward because there are still a lot of uncertainties, and we are trying to quantify those. And this was an excellent work done by Julia Bliss, also in my group. She was looking at the astrophysical uncertainty. So you see here in blue all the variability in the abundances due to different possible astrophysical conditions in the neutrino-driven neutron-rich ejecta in supernova. And also she looked at the impact of alpha N reactions that are very important in this WICAR process here. Okay, so this is a way of constraining things. We look also at simulations. So let me say something about the simulations of supernova and neutron star mergers. So for supernova, for the standard supernova, neutrino-driven supernova, we don't get so high. So it's like this figure from Julia. So we get up to silver, but not the heaviest R process elements. So if we want to produce the heaviest R process elements, we need something a bit more exotic. And this is magnetorotational supernova, where the magnetic pressure can eject matter very fast before neutrinos change neutrons into protons. And this has been suggested a few years ago, and there has been some 2D and 3D simulations with a parametric neutrino treatment. And now we have analyzed, based on the simulations of Martin over Gaulinger, who are simulations with the state-of-the-art neutrino transport, we have analyzed the nucleosynthesis, and we found this very rich nucleosynthesis. And only with accurate neutrino transport, we can really say something about the WICAR process or the neutrino P process. And you see here the results, was also done by Monte. You see the abundances, and these are different models with different rotation and magnetic field. And the red one corresponds to a model where the magnetic field is the strongest. This is based on 2D simulations. Of course, 3D is important, and only now are the first 3D simulations with accurate neutrino transport in the market. Those are the ones from Martin over Gaulinger and Takami Kuroda. So they were both postdocs in my group, and we had a lot of fun, and we learned a lot of things. So it's exciting, but very, very complicated. Okay, so let me move to neutron star mergers. Here we are still a work in progress. We are trying to move from 3D simulations with the Einstein toolkit to 2D simulations. This is the work of Federico and Max. You have the pictures of them there. So hopefully in the next workshop, they will present the results together with other collaborators. And in neutron star mergers, we have the initial dynamical ejecta, but it's important to follow the evolution for longer times and see what happens with the disk. Hopefully you will see results soon. We are still dealing with some problems, but let me just very briefly summarize the different kinds of ejecta, although it was already mentioned before. So we have this early tidal ejecta and shock heating ejecta at a few milliseconds after merger, then at longer time scales, when an accretion of this forms surrounding the compact object, we can have a neutrino-driven wind and also the latest integration of the disk. So these all produce different nucleosynthesis, as you know, and we have also analyzed that. This was work done with Oleg. So it's so nice to present results that many people in the audience are there and made the results. So here you see the nucleosynthesis moving up. You see here a lot of matter. This is coming down because of fission. And so this is from a simulation of a Stefan. So it's the matter that is ejected here in these tidal torques. And it's very exciting because it's very robust, like it's supposed to be. So these are different simulations for different masses of the neutron star and neutron star black hole even. We get always the same pattern. Okay, this is also exciting, as you know, because the matter, when it beta decays, produces energy. So this is the energy generation that I calculated already in 2010, 2009. And that then was used by Dan Kassen to calculate this light curve for the kilonova. And here you have the observational points from the observation of 2017. So you all know that this is just coming from the dynamical ejecta, and you know that we have seen the kilonova and we need to put everything together, and we can use the kilonova also as an observable to constrain the neutron star mergers. Other thing that we have looked at based on the simulations of Albino Perego, that was the work done by Derek Martin, the nucleosynthesis, is what happens with the neutrino-driven wind. So the same as in supernova, neutrinos transform neutrons into protons, and the ejecta is not so extreme neutron rich, but it's still more neutron rich than in supernova. But you see, we stop here at n = 82 and then decay to stability. This is in principle very exciting because, so this is also from our paper of 2015, you can combine the different ejecta. So this is coming from the neutrino-driven wind, and this is the dynamical ejecta, both from the previous figures that I was showing to you. And the different times is when a black hole forms. Of course, if you form a black hole earlier, then you have less neutrinos coming from the neutron star in the center and pushing matter out. So you have more matter if the neutron star survives longer. And you see that if you combine both, then you can reproduce the whole R process abundances. And here you have the combination of both. And now you have to remember what I was saying before. We have an strontium component and an europium component, and we have this kind of tooth patterns in the star. So we have kind of a Sneden and on the star. And we, depending on how we mix these two components, we can also explain these two kind of patterns. So I think this is also very exciting, and we have to think more about that. This is what also Stefan was saying, a long time evolution, very long, and also looking at the mixing. So this is really challenging problem, but that's nice to have challenge. And here is also a calculation of Oleg. So Oleg calculated the light curves for this wind and dynamical ejecta. If we take into account only the wind, it's more like blue. If we take the wind and the dynamical ejecta, then it picks later and the infrared. So this kind of agree, even if the velocities don't agree at all, but kinds of agree of having two components. So we were suggesting of the possibility of having two components already in 2015. Let me see. Yeah, and we know we have this strontium component because we have also seen a strontium in the light curve of in the spectra of the kilonova. So this is the spectrum of the kilonova. So if it's just a black body, it would be like that. You need to have these features that are due to a strontium to explain the spectrum. So that was work done also by Camilla Hansen. Okay, so this was a bit fast, some simulations that we have done on how we have compared or calculate the nucleosynthesis and try to do the kilonova calculation in a very simple way. And now I would like to talk shortly also about a big problem or a big challenge that it fits nicely with being virtually in ECT star. And it's the microphysics that enters in the simulation. So this has a huge impact on the amount of matter that is ejected and on the composition of the matter, but also the nuclear physics that enters into the nucleosynthesis. So I will go very briefly through that. So the equation of a state in the neutron star mergers, it has a big impact on the amount of matter that is ejected. Those are full GR simulations from the Frankfurt group, where Federico was very involved and doing the calculations and the analysis. And you see here 3 different equations of a state, and they eject very different amount of matter. That's why the kilonova in the 3 cases are different. So these are like for the 3 different equations of a state, and there are different systems with different masses of the neutron star. So we can somehow try to link things together, but I think at the moment this is impossible because there's too much degeneracy. So we need to improve a lot the simulations before doing strong conclusions. And also one thing that was pointed out by Stefan, and I agree completely, and we will hear more in the next talk, is the impact of neutrinos. So this was also based on full GR simulations, was done by Derek and by Albino Perego. And what they did was change the luminosity of neutrinos. And you see, if you have a lot of neutrinos, you are going even to kill the 3rd peak in the dynamical ejecta. Okay, so we have also looked at the equation of a state and neutrinos in the context of core collapse supernova, and indeed the new things that we have in terms of equation of a state. For example, we tried them first in the core collapse supernova context, since this is the simulations have more details and more microphysics and are better under control. And here is an example. This was done by Carlos Mates during his PhD. So he changed to 3 different neutrino schemes, always with the flash code, always the same hydro, but different neutrino schemes and 3 different equations of a state. So this gives us an idea of the uncertainties that we have because of the neutrino treatment and because of the equation of the state. So the microphysics is making an impact on the evolution of the shock here without explosion, but also on the luminosity. So also on the nucleosynthesis, since the nucleosynthesis strongly depend on the neutrino properties. I have this slide here, but I think I won't say almost anything because Sabrina Hood is going to talk about that tomorrow. Sabrina and Hannah has looked at the impact in a very systematic way, impact of the equation of a state on the supernova explosion. So here's the evolution of the shock, and here is the contraction of the proton neutron star. And this is really the first systematic study where they use the same underlying physics and vary one by one the different nuclear physics properties. And they found that the contraction of the proton star is ruled by the effective mass. But Sabrina will tell us more tomorrow. Okay, so in addition to the microphysics that enters in the simulation, we have also the uncertainties in the nucleosynthesis. So, we need to know a lot of different nuclear physics of extreme neutron-rich nuclei, nuclear masses, beta decay, reaction rates, and fission. And we are going to have many exciting talks. So you have seen also a lot of results from Rebecca, Matt, and Nicole. And Gary will talk also about fission. So, but I want just to show also the results from Dirk here, where he calculated using the masses. No, it's not written the reference, sorry. From the density functional theory, different masses, and then he found for mergers and for magnetorotational supernova a certainty band for the abundances. I'm almost done. Okay, so just 3 observational results. So we want to use observations to constrain the simulations and understand better the microphysics that we are using. And here there are 3 observational highlights. One is the European stars. These are, when we analyze these dwarf galaxies, we realize that in Fornax, there are a few stars with high European abundances. So these are the most European rich stars ever observed. So you have here European over iron, the figure I was showing before, and in gray is the Milky Way. The stars, the green stars are the Fornax stars, and there are these 3 yellow points. And they have a lot of European. So the European over iron is very high also for these reticulum 2 stars, but the total European is not so high for those. So these are much more exact. And this is very exciting because these are R-process rich and high metallicity stars. And we try to find, so that was also with Moritz and Camilla, we try to find out if this is R-process, S-process. So here is the ratio of baryon over European. And these are S-process models, so it should be at these metallicities and at these values. So this black star here is an S-process star, and those here are fitting here R-process. So these are 3 neutron star merger models for the dynamical ejecta. These are magnetorotational supernova, the Winterland, the Overgaulingen model, and this is ejecta from the disk after the neutron star merger. Of course, the uncertainties are very big due to the nuclear physics. Actinide will start. I have no time, and I want just to finish with also showing something from Benoit. It was a very nice collaboration with many people involved, and Benoit and Marius did an amazing work putting all this together. So this is the ratio that we would observe, or that we have from meteorites, from these 2 radioactive isotopes, and the different positions here corresponds to different astrophysical conditions. So here is again the magnetorotational supernova, and the different symbols correspond to different nuclear physics. So you see, one can combine everything, and if one has a golden ratio, one can use it to say, for example, that the R-process that contaminated the cloud where the sun was formed was coming probably from the disk of that forms after a neutron star merger. This is an idea of how we can learn more, but of course there is a lot of room for improvement. And with this, I just leave my conclusion slide because I'm 1 minute over my time. Thank you very much.
Thank you so much, Amadena, for that lovely talk. So the floor is now open for questions. So go ahead and type them in the chat, or you can raise your hand. So I was wondering if you could say a couple more words, I'll kick things off, about the Magnetorotational Supernovae. So it seems like pretty extreme conditions are needed to make the third peak. What portion of our process do you think could come from these events?
So I would say we cannot answer that question yet. We need better models because, for example, in the models, here, in these models, for example, we have this yellow line. So here we are producing only a weak hour process, but this was matter that was ejected 1.2 seconds after bound. So it's a late ejection. So it's a system that it's very dynamical during seconds, not like the supernova you do the first second. So it keeps accreting material. The neutron star changed the form, and here we saw that due to angular momentum redistribution, some neutron-rich matter from the outer layers of the neutron star enters the channel where the matter can get ejected. So I think we need to explore different configuration of the magnetic field. We need to explore more in 3D models and also the long time evolution. So it's very challenging. So I don't think we can answer the question, but it's clear we need something like that. And I think Frieder will talk more about that on Friday, that this is also a way of explaining, and also like from this figure of Benoit, it's a way of explaining what happens early in the galaxy. So it's an excellent candidate, but let's see.
Great, thank you. Any other questions or comments for Amadena? So in addition, as Chris mentioned, in addition to the time after each talk, we will also have time in the morning or the next morning for our European friends to ask questions. So continue to think about the talks and there'll be additional time for discussion. But indeed, we do have a talk or a question from Chris. So go ahead, Chris.
Yeah, I just have a quick question. There's the observations seem to indicate that our process has at best, like two different components, where they look at the heavy R process and the ratio of the heavy R process elements is the same in every star that they look at. And then you can have a different one for the light R process. But do you have is there a picture that you think works to kind of explain that kind of the fact that there's not that much variation in the stars that we observe as far as the R process?
Okay, so I would say I'm not so sure that it's so robust. So we always saw this figure mini 2. So not today, but usually I saw this figure, and there the y-axis is huge. So it's not so robust. So there is some room for variations, and we see there are some variations. So one needs to, I think, to get better observations and look at them carefully. And there are some trends that could be linked to different environments. And I also think, at the end, you have something that runs far from stability and decays. So it's the same independent wherever you are. So at the end, it's like, I think the nuclear physics governing this robustness, so that it happening always far from stability, decaying, and at the end, the final abundances are given by beta decays and the last neutron captures, and this happens more or less the same in all environments. But I don't believe it's always robust. So you can see there are these onda or R-limited stars, and there are also other variations that are seen in observation. So there are a few of them that are robust, but not all of them. So I think this is also very exciting, and we should move also farther in that direction.
All right, well, thanks, Chris, for the question. Thanks, Amadena, for a nice talk. And we will be ready to move on to our next speaker, who is Jonah Miller, will talk about neutrino transport in simulation. So, hey, Jonah, how are you?
Hi, I'm good. Hope everyone is doing well. It's been a really great talk so far, or really great meeting so far. So I want to start by just mentioning that the work I'm going to be talking about is big effort. So a lot of people have been involved in the work I'm talking about, many of the people in this call, in fact. And I wanted to highlight especially 3 junior researchers who I'm going to mention a little bit throughout the talk. Trevor Sprouse, who's giving a talk later in the workshop and is a postdoc at Los Alamos now. Sanjana Curtis, who was a graduate student at Los Alamos and is now a postdoc in a joint appointment at Amsterdam and Santa Barbara, and Shomi Day, who is currently a postdoc at Los Alamos as well. So Stefan and Almudena already gave really nice introductions to this, so I won't spend too much time on it, but I did want to briefly set the stage for sort of the story I'm going to tell, which is when you have a merger event, as the stars get close, they tidally disrupt each other and material streams out in these tidal spiral streams, which is the tidal ejecta. And some of that material falls back onto the remnant and forms an accretion disk. Some of it escapes and becomes the tidal ejecta. And in the animation I have on the left, the central remnant is a hypermassive neutron star, but you might also get prompt collapse to a black hole. You might get a stable neutron star, whatever. On the diagram on the right, I am showing one possible scenario for the GW170817 case, where I've highlighted the viewing angle we saw the event at. And the things I want to highlight here are that you have that this accretion disk drives this polar wind in this sort of hourglass shape. And I've labeled this neutron poor. I'll explain what that means. It's not really neutron poor. It's relatively neutron poor. It's more neutron rich than symmetric matter, and the neutron rich tidal ejecta in this expanding donut far away. And so, also, since Almudena also just introduced nucleosynthesis, I won't spend too much time on this. This is an animation of a nucleosynthetic trace that was done with Skynet, courtesy of Jonas Lipner. But the thing I want to highlight is that the afterglow that's produced by the radioactive decay of the heavy elements is produced depends on the elements that are produced. And this is because these elements have different opacities. So the elements in the rare earth peak between the second and third peaks are relatively opaque to visible light, so they produce a redder afterglow. And the elements, if you don't have those elements, then you'll get a bluer afterglow. And indeed, this is what we saw in the 2017 event, as Stefan already showed. So this is a composite image of that event, where the blob in the center is the host galaxy, and then the arrow is pointing at the kilonova afterglow. And at the beginning of the day of the observation, it was blue. 4 days later, it was red, which suggests that there are multiple components to the observation. There was somewhere in the source event, there was the red ejecta. The tidal ejecta almost always produces a red afterglow, but somewhere else there was something less lanthanide rich, fewer rare earth elements, and that would produce the early blue peak. So I'm going to focus for the rest of the talk on the accretion disk, and in particular on the importance of neutrino physics. So the first thing I want to highlight is that neutrino transport really, really matters in these problems. And to get this point across, I have this thought experiment that I ran. And the basic idea is you start with matter in sort of neutron merger disk conditions, high densities, but not as high as nuclear density, high temperatures, something like 1 to 10 MeV. And what I've done here is I've taken this gas and I've put one spot where there's a low electron fraction and one spot where with a high electron fraction. As a reminder, electron fraction is kind of a good measure of how neutron-rich material is because it's the ratio of electrons to baryons. And so if it's low, you're more neutron-rich. If it's high, you're less. And then I put a membrane around each of these spots so the fluid can't mix. And then I let neutrinos go. And if you do real neutrino transport, what you'll find is that neutrinos can carry electron fraction from one location in the gas to another location. And so they completely control and set what the electron fraction is in the gas, as shown here as they drive the system to equilibrium. And I'll note that the reason that the electron fraction in the entire gas seems to change as the simulation goes to equilibrium is because the simulation is going into equilibrium between the gas and the radiation field. So there's some lepton number conserved carried in the radiation field, which is not shown in this picture. So how much does transport matter in these systems? Well, there's been a lot of literature on this topic over many years. I highlight some of the authors at the bottom of this slide here. And what this slide is supposed to show you is what regimes you get in accretion disks and whether or not, and how important transport is for those systems. So on the x-axis, I've got accretion rate, which for binary neutron star mergers, you can directly relate in sort of, well, I should say you can wishy-washy relate, if you squint, to the mass of the remnant disk at the beginning of it, at the end of the in spiral and the merger, but before accretion really starts. And on the y-axis, I've got optical depth, which I'm just using as a proxy for the importance of all neutrino interactions here. And so if you have very, very low accretion rates, say like XRBs, then no nuclear processes matter at all. You turn up the accretion rate a bit, and you can get to something like magnetorotational supernovae or collapsars, and these systems are rather emission dominated. So opacities haven't yet really turned on, but nuclear reactions have, and so you get neutrino emission. You turn up the accretion rate even further, you can get to something like 1/10 of a solar mass in the accretion disk. That's about the regime of neutron star mergers. And although the optical depth is still low, in quotes, you do in fact get absorption matters here. And those systems, for those of you familiar, they're accreting at approximately 10⁻³ neutrino Eddington. So they're at something like 10⁻⁵ photon Eddington. But if you replace the photon cross-section with the characteristic neutrino cross-section and do the same calculation, you find it's about 10⁻⁻³. And finally, if you turn things up even further, you can get some very extreme cases where you have black hole neutron star mergers with a rapidly spinning black hole and just the right mass ratio. You can find that the neutron star tidally disrupts before it plunges into the ISCO, and you can get a complete tidal disruption. So you can get something like 40% of a solar mass, like half the neutron, a little bit less than half, like maybe 1/3 of the neutron star in an accretion disk. And I just wanted to mention that Sanjana Curtis is working on these problems, so stay tuned for a publication from her sometime in the near future. So what do you need to do to get this physics right? Well, you need general relativity. In the simulations I'm going to talk about, it's just a rotating black hole spacetime, stationary spacetime. But for those very massive disks that I just mentioned, for example, that's actually not good enough. You should really be doing dynamical GR. You need plasma physics of some kind. Here we approximated as ideal MHD, but in principle there are things like magnetic reconnection. Resistivity isn't totally irrelevant, and in parts of the simulation where the densities are very low, for example, in the jet, really the fluid approximation breaks down, and a kinetic theory would be more appropriate. On the nuclear physics side, the hot gas in the disk is treated as being in nuclear statistical equilibrium, so it's encapsulated in the tabulated nuclear equation of state. However, this is no longer appropriate as the outflow cools, and then you must really treat the non-equilibrium nuclear physics via a nuclear reaction network, as Almudena just talked about. On the radiation side, material is totally opaque to photons. It's just part of the equation of state in the plasma. But the material is not opaque to neutrinos, as we just talked about. And neutrinos can change the composition of the material. So the neutrino transport, you have to really solve it. So just as sort of proof by intimidation, here's the general relativistic form of those equations for each of those pieces of the simulation that I just talked about, or of the modeling that I just talked about. And if you're interested in trying to do some of this modeling, you can. So we have Nublight is open source LANL code. You can find it on GitHub, download it, try it out. If you run into trouble, you can always reach out to me or another developer and get some help. And Nublight does GRMHD coupled to Monte Carlo neutrino transport. So without further ado, then let's talk about the 2017 event that I kind of presented at the beginning of the talk. So this is a simulation that we ran of that event. The top is zoomed in, the bottom is zoomed out. The color is electron fraction, purple is low, orange is high. The left column is a colloidal slice of this 3D simulation. The right column is an equatorial slice. And the things I kind of want to highlight is at the beginning, you start with this compact torus that's sort of orbiting around the black hole. But as you let this thing go, magnetorotational turbulence drives angular momentum transport, and the material forms this nice, beautiful disk. That disk drives this outflow in this hourglass shape, as you can see kind of on the bottom left panel. And you also notice that something is tunneling through that hourglass, which is the ultra-relativistic jet. And you'll also notice that there's this very interesting angular structure where the equator has a lower electron fraction, and the poles, as you go towards the polar region, you get a higher and higher electron fraction. And that is actually set by the neutrino physics. So here's a movie which is, bear with me, this is a very complicated figure. What I'm plotting here is the emission rate minus the absorption rate of, on the left, electron neutrinos, and on the right, electron antineutrinos. And the color bars give you, red is more emission on the left, blue is more absorption, and on the right panel, purple is more emission and orange is more absorption. And I've chosen these particular colors so that the reddish-er colors mean electron fraction is going down, and the bluish-er colors mean electron fraction is going up. And ignore the fact that there's this complicated inverse cinch thing. It's just a sine log, essentially. And what you see is at the beginning of the simulation, at very early times, right after the merger, both emission and absorption actually matter quite a bit, especially for the electron neutrinos. Electron neutrinos are emitted in the core and absorbed in the equator and absorbed in sort of the corona region in the higher latitudes, and this carries electron fraction. So electron fraction is going down in the equator and higher at the higher, and going up in these higher latitudes. At later times, after things have cooled down a bit, the accretion rate has gone down, then you eventually reach this place where emission is the dominant factor, and the electron fraction is set by the balance between the emission of electron neutrinos and the emission of electron antineutrinos. And this angular structure that's set by this neutrino transport does in fact translate into the outflow. And so you get this beautiful, almost linear angular dependence on the electron fraction in the outflow, which translates to different nucleosynthetic yields. The more equatorial outflow is more neutron rich and might produce a red kilonova. The more polar outflow is more neutron poor, lanthanide poor, and might produce a blue kilonova, which is what we found when we actually did the photon transport afterwards. And I want to highlight again that this story really does change as you turn up or down the accretion rate. So on the bottom left here, that is a picture of Shomi De. She did this really nice paper in collaboration with Daniel Siegel, where they worked on sort of the lower end of the accretion rate spectrum, so sort of collapsar disks and very low mass neutron star disks. And on the top right, I'm again highlighting Sanjana's work on these very high black hole neutron star merger cases. In both those cases, this angular momentum, or this angular structure in the electron fraction does seem to hold, but whether or not you get a blue or a red or what the yields will be can look very, very different. So that's kind of the basic story, but I wanted to dig in a little bit deeper with you all about what really does set that angular structure. It's one thing to say that neutrino absorption matters for that, this is true, but why the particular values of YE that we see. And to get into that a little more deeply, I'm going to look at a collapsar disk, a disk formed after the core of a massive rapidly rotating star collapses to a black hole, which means that it's really in the emission-dominated regime. That said, the story I'm going to tell you, whether or not it's emission-dominated or whether absorption matters, that is going to be a component of the details, but the overall thing I'm going to try and convince you of will hold regardless. So let's go. So the thing I wanted to highlight about this simulation is that even after the disk forms what's called a quasi-stationary state, where the accretion rate is kind of a power law of time, and it seems to have forgotten its initial conditions, the electron fraction is still often very far from equilibrium. So what I'm plotting on the top here on the left panel is the electron fraction in equilibrium, which does still have an angular structure to it. And on the right, I'm showing the difference between that electron fraction the physical electron fraction actually measured in the simulation and the equilibrium value. And at the end of the talk, if you're interested, we can talk about how I define equilibrium. That's actually somewhat subtle, but for now, just accept it. So that's one fact I wanted to point out. Another fact I wanted to point out is that these pictures I'm showing hide a lot of the complex turbulence that's going on, because I've taken a slice, or I've averaged over the over phi, the azimuthal angle. But these are really turbulent problems. And so on the bottom right here, I'm showing tracer particles, basically Lagrangian fluid packets advected with the flow, and their paths. So the y-axis here is latitude, the left panel is time on the x-axis, and on the right panel, the x-axis is the cylindrical radius. And you can see these paths are basically random walks. They're very, very stochastic. So that leads to perhaps a toy model about what actually happens in these systems, these two facts. And here's kind of the idea. This is one example of what it might be, to give you kind of something concrete, but it can also go in other directions. So suppose you have some equilibrium value. The y-axis in this cartoon is the latitude, distance from the equator. And near the equator, the equilibrium value of ye is low. Further from the equator, the equilibrium value of ye is higher. And now stuff is moving around. So for example, you might have a particle, some fluid packet that starts near the equator and moves up towards higher latitudes. It does so somewhat stochastically. So there's some stochastic rate of change where it's slowly moving up as it random walks. And if it does so, it wants to go towards the equilibrium value of the electron fraction. Whether or not it can depends on how fast it's moving compared to how quickly the neutrino physics is happening, how quickly the weak physics is going on. And so as it moves up, it's absorbing or emitting neutrinos. And if it's emitting and absorbing neutrinos very quickly, then it'll keep track with the equilibrium value. But if the neutrino physics is happening less quickly than the stochastic motion, then it won't. And you might end up with a lower electron fraction at higher latitudes than if you were in true equilibrium. And so it turns out that you can actually try to measure this. So this is another complicated plot. My apologies for that. This plot is measuring the timescales of weak processes that either raise or lower the electron fraction versus the timescale of this sort of random walk through the disk. And so on the left panel, I'm plotting the ratio of the timescales of electron fraction either going up or down. When the white region is where the where you actually are kind of in weak equilibrium, that's sort of in the polar region of the simulation, the equatorial region of the disk. But at higher latitudes in the corona, this is not the case. At this particular time in the model, you want to go to higher, electron fractions want to go up. That's what the purple means. So it's out of equilibrium. On the right side, on the right panel, the top right half of the panel is the ratio of weak changes to turbulent motion that would want to decrease the electron fraction, and the bottom right half of the panel is increased electron fraction. And the point I want to make here is that if it's very red on the right panel, ye is frozen out. This is the electron fraction, you're way out, the ye is happening so slow, changing so slowly, the neutrinos are having so little of an effect that dynamically it's not relevant, but you need to track it with, say, a nucleosynthesis network. In the blue region in the right half of the plot, that's where you're in weak equilibrium, and the weak physics is happening much more quickly than the turbulent physics. But there's this white and sort of orangish reddish region where they're in competition, and where the electron fraction in the disk is really set by the competition between these two timescales. And you can actually plug this into a semi-analytic model where you just basically say ye is a function of these rates and your latitude, and you can measure that in a model and actually try to sort of in two ways, one with measuring sort of these Lagrangian fluid packets, and one just measuring what ye actually is. And they actually agree very nicely. So this black line that I'm showing on this plot on the right is in fact this semi-analytic model that kind of has predictive power about what the electron fraction should be as a function of latitude, coming from this sort of toy story that I was telling you before. So that leads me to my conclusion, which is that we need both general relativistic radiation magnetohydrodynamics and neutrino transport. What matters for setting the electron fraction in these outflows is neutrino emission, neutrino absorption, and the competition of those weak processes with the fluid dynamics. All of these things matter. And of course, I don't need to convince you all that neutron star mergers are likely a source of heavy elements in our universe. And hopefully I did convince you that disks can produce the blue component of a kilonova. Not to say they're the only source of a blue component, but they may be one. And as I've hopefully shown, there's a large diversity in the outflows of these disks and in disk physics. This angular structure does seem to be generic, and it's set by this competition. So, and there's more coming from some of the people I mentioned. I look forward to Trevor's talk later in the workshop, and look forward to publications by Shomi and Sanjana in the future. Thank you.
Great, thanks so much, Jonah. Yay. Questions, comments for Jonah? I'm going to start things off by asking, I hope you don't mind, a slight technical question. What reactions are you using to calculate YE in these regions? What exactly is the input there?
Oh, yeah. I had a backup slide for this, and it's not in this particular slide deck. But so for emission and absorption, it's charge and neutral current interactions. So things like electron capture and inverse electron capture. We also include scattering off of nucleons and electrons and heavy nuclei. The scattering interactions are, we found that for these disk problems, they're actually not very important. Absorption seems to be sort of the dominant non-emission process. And we use basically all of the interactions that are in the classic Burroughs-Reddy-Thompson paper with corrections provided to us by Adam Burroughs. So things like stimulated absorption are included. We do include neutrino annihilation approximately, not as accurately as we would like.
Okay, thanks. And how do you get the composition to do the scattering on nuclei? Is this just an NSE kind of contribution, or are you doing one heavy nucleus?
No, we assume it. We assume NSE. We assume NSE. Okay. So, and it's sort of both. So we work out what it is in NSE, and then we average over all the nuclear masses, over the nucleus masses, and then we scatter off of the average. So there's definitely some improvements that could be made there.
Okay, great. So we have one hand raised, and there's a couple questions in the chat. So Stefan, why don't you ask your question first, and then we'll go to the questions in the chat.
Okay, very nice talk, Jonah. Just a question. I understand that you can probably eject a large diversity of material properties from different types of disks. Say, what type of disks would you need to eject something that has electron fractions around roughly 0.15-ish or so?
Yeah, so low mass disks typically produce the lower electron fraction outflow. I mean, as I just mentioned, the equatorial outflow from these disks is almost always pretty low, but the lower the mass of the disk, the less neutrino, well, there's kind of a sweet spot, right? You don't want to be at accretion rates that are too low because then nuclear physics don't matter. But something like 1% of a solar mass or less, that's where you can that's where emission matters for neutrino physics, but not the absorption really. And in those cases, you can get very low electron fraction outflows because the absorption doesn't raise the electron fraction in the corona. So there's I want to highlight again, Shomi and Daniel's paper. They have a really nice paper where they go through like a range sort of logarithmically of accretion rates and masses below about a percent of a solar mass in the disk, and they show how these things change. They're doing a leakage scheme, not Monte Carlo transport, but they're doing it in a regime where I think that's well motivated.
Okay, thanks.
Okay, so we have a couple of questions in the chat. Nicole is asking about different types of neutrino transport. What are the advantages and disadvantages of using Monte Carlo versus other treatments?
Yeah, great. So Monte Carlo has the advantage, of course, that it is, you can kind of split these transport methods into sort of two categories. One where you solve the full Boltzmann equation and one where you do some approximate treatment. So on the approximate side, the most popular state-of-the-art techniques are moments, radiation diffusion, which is a limit of the moments essentially, and leakage. And there's been a lot of thought on when these things are appropriate. What I will say is that in very high optical depth regions, leakage is less appropriate. Moments and diffusion are fine. In the free streaming regime, moments do very poorly. Leakage does quite well. And there's the intermediate regimes where you really need the Boltzmann equation, because moments, for example, have these problems where because you're treating the radiation field as a fluid, you can get like radiation shocks and like laser effects that aren't really physical. Whereas for a full Boltzmann solve, you won't have these issues. Boltzmann, if you do the full Boltzmann solve, of course, it's very expensive. Monte Carlo is probably the cheapest of these approaches. But it has the problem that it performs very poorly at high optical depth. And so if you want to span all ranges of optical depth, you need something new or something better. So something like discrete ordinates or like a spectral Boltzmann solve where you really solve the Boltzmann equation on a grid. That's extremely expensive because then you're solving a full 6+1 dimensional PDE system. At Los Alamos, we've been pursuing, and others as well. So for example, Francois Foucault has been pursuing a hybrid method where you do moments when appropriate, you do Monte Carlo when appropriate. You basically close your moment scheme with a solution to Monte Carlo or with an appropriate analytic closure. And we've been pursuing a similar idea in this work called MockMC. So Ben Ryan and Josh Dolan's put out this very nice paper on this hybrid method where you close a moment scheme with a long characteristic solve. So I think the future is really full Boltzmann solvers, and I think the future is probably not Monte Carlo as I presented it here, because we can't treat things like a hypermassive neutron star very accurately.
Okay, thanks. And for one final question, we have Gail's comment. She would like you to say a couple words about the current expectation about the relative amounts of our process that comes from a black hole neutron star merger versus binary neutron star merger.
Okay, I will try to do my best to answer that question. That's a deep one. So
yeah, and your time is up, so you got to do it fast too.
Do it fast. Okay. So I think sort of it's reasonable to expect that you're going to get some fairly large fraction of the disk in the outflow, as like the Siegel and Metzger papers sort of demonstrated. You can get a very large fraction of the disk becoming gravitationally unbound. So what really matters for how much R process you get is, well, what is the electron fraction in the outflow, and also what is the mass of the disk that you start with. And just to give you a hint, I think for very large disks, it turns out that the outflow is too high of an electron fraction to produce meaningful R process. Whereas for very light disks, you get a lot of R process material, but it's very, but there's not much disk. So the sweet spot probably is for sort of equal mass neutron star binaries. That's where you're going to get the most.
Okay, great. Thank you.
Thank you.
Yeah, thanks for all these questions. Thanks for that great talk. I think now we're going to move on. We've heard about how important neutrinos are, and now Mengru, I think, are you here, Mengru? You will go ahead and talk about oscillations and the role that they play. I think you're still muted. I can't hear you.
Sorry, take a while for me to.
Okay, great. Thank you. Go ahead.
Okay, thanks for the for giving me this opportunity to talk about neutrino flavor conversions in neutron star merger remnant. So I think the previous three speakers has already mentioned a lot about neutrinos and how important they are in neutron star merger environment. Okay, so I just put one punchy slide to summarize some basic of it. So basically, we know that merger remnants are very strong neutrino emitters for the MEV thermal neutrino ones. Okay, and most of them may come from, say, the central hypermassive neutron star in the center after the merger if it survives, or also from the accretion disk that surrounds a hypermassive neutron star or a black hole that was just mentioned by Jonah. And one key feature, and from those two plots that are shown here, that you can see the neutrino energy luminosities for different flavors, different colors can be up to, say, a few times 10 to 50 ergs per second. That is comparable to supernovae. And the mean energies could be having a hierarchy and ranging between around 10 to 20 MeV each. Okay, and one critical thing about neutrinos coming from merger remnant is that we know the merger remnant must protonize for some period of time because initially the two neutron stars are very neutron rich. We heard from Stefan that is YE mostly below 0.1. And when you heat it up from the violent collisions, then you raise the temperature. So you would have a lot of positron capture coming off and then produce a lot of electron antineutrinos in the beginning period, as shown in this figure in the left here. Okay, so those are electron antineutrinos, those are the electron neutrinos. Okay, so you can see they clearly dominate a lot of electron neutrinos. Okay, so for at least some tens of milliseconds. Okay, and we also heard that the neutrinos can strongly or importantly affect the neutron richness of the ejecta, and by those neutrino absorption reactions on nucleons, and those were already discussed. Okay, so one big question that the neutrino flavor conversion community is aiming for is what are the potential impact of the neutrino flavor oscillations on the merger ejecta and the nucleosynthesis. All right, so this is a difficult question if we want to solve it fully. Okay, so we already, Jonas hinted that if we want to solve, say, a full Boltzmann solver of neutrino transport, then we need to solve this 7-dimension Boltzmann equation. Okay, but if you want to include the flavor oscillations of neutrinos, then you need to do a bit more, okay? Because you basically, what you need to include is you basically need to extend your a real quantity of neutrinos, say, only evolving the occupation numbers, those F. You need to extend to the lowest order into a density matrix that contains also the off-diagonal elements here. Okay, so this is basically, this row is basically a regularly transformed flavor density matrix. And so those are the components that you usually evolve in the neutrino transport equations. But if you want to deal with flavor oscillation, you need more. All right. And then in addition to this part, then you, of course, you need to also expand your right-hand side, that is your source term. Okay. So when you include the oscillations, then you need to include typically effective neutrino Hamiltonians that consist of 3 different contributions. The first one is coming from the vacuum neutrino maxim. The second one is coming from the neutrino forward scattering of nucleons and electrons and positrons. The third term that is mostly complicated is coming from the neutrino forward scattering among themselves, as depicted here. All right. So this H nu contribution is basically proportional to, say, the strength of it is basically proportional to the Fermi coupling constant, that is the nature of weak interaction, and multiplied by the number density of neutrinos. All right. But one important thing that you can see here is that this H nu contains the density matrix of neutrinos themselves. So that basically tells you that, okay, this is a nonlinear coupling problem. Okay. So then when we say that, okay, if this is a nonlinear coupling problem, and then if we are in the neutrino dense environment where the H nu can be much larger than, say, HVAC or HM or even the collision rates, then we know that this kind of system is basically equivalent to a strong coupling system, and that means that collective behavior can emerge. Okay, so more precisely, neutrinos with different momenta can oscillate collectively. Okay, so this was known for several years, since almost 20, 30 years ago, due to the effort in understanding supernova neutrinos. All right, so We know that solving this full equation of motion is very, very super challenging, but how can we do before solving that? Okay, so what we can do is the first step, we can linearize the equation of motion. Now I dropped the collision term. And then we can, by linearizing the equation of motions, then you can try to understand, let's say, if you have a small off-diagonal term, that off-diagonal terms are those here, and that signifies the flavor oscillations potentially introduced by making oscillation, for example, then how those small off-diagonal terms can grow in space and time. Okay, so this can be completely done through linearized instability analysis. So by we say instability, that is meaning basically saying that given a small perturbation of diagonal, then how fast it can grow. Okay, so this is basically once you do this, then you can derive a dispersion relation coming from this equation of motion. Okay, and then you can say, for example, if you look at a particular Fourier mode, that is a particular wave number. Let's say if I assume that kx and ky are 0, and then I only look at the wave number, finite wave number kz, then I can solve this dispersion relation and then try to find what is the corresponding frequency solutions that satisfy this linearized equation. Okay, and if you find, say, the complex omega, if you find a frequency that satisfies the dispersion relation having both having an imaginary part, then that means that this flavor situation or the initial configuration of your flavor system is unstable. So that would tell you that even a very tiny perturbation in the off-diagonal elements, then it will exponentially grow. And the growth rate would be basically the complex part of the omega. Okay. So now, if we do this exercise for different configuration of, say, your neutrino distributions in the system, then what people found in the past, over the past few years, was that the so-called fast neutrino flavor conversion can happen within very short length scale of roughly centimeter-ish. Okay, so this length scale is basically set again by the neutrino-neutrino forward scattering Hamiltonian. So that is inverse of the Fermi times neutrino number density. Okay, so this can happen provided that there's a so-called local angular distribution closing. Okay, so put it in plain words, that means that basically if you look around of your surrounding in the 4-5 angular space, then you see more electron antineutrinos than neutrinos in some solid angle, while more electron neutrino than antineutrinos in other ranges. Okay, okay. So this is what the people found and recently proved strictly by Morigana in 2000, just this year. Okay, so why is this relevant for neutron star merger remnant? That is because, for example, we found together with Irene and Bora, we examined a very simple parameterized toy models and then basically found that merger remnant host particularly favorable conditions for this faster flavor oscillation to occur, or say to have ubiquitously the neutrino angular closings. Okay, and this is due to two facts. The first one is that, as we say in the beginning, the merger remnant must protonize. So that means that you have more electron antineutrinos coming from than electron neutrinos. And because typically the environment is more neutron rich, so you have a smaller, say that your nu E bar would be mostly more forward peaked compared to mu E. Okay, so that is, so when you couple those two facts together, then wherever you look on top of your merger remnant outside your neutrino emission surface, then you will see, say, some pinkish region here, you have more electron antineutrino, while in some more like bluish region, you have more electron neutrinos. So this would be telling you that there's a faster flavor instability. Okay, so yeah, so this plot just tells you that, yeah, just shows you an example that we do some simple model, and then what we found is that this inverse growth rate, the growth rate of the flavor instability can be really in the order of centimeter or even shorter. Okay, everywhere above the merger surface. The neutrino emission surface inside in the merger remnant. Okay, so that's nice, but then how do we go from there? Okay, so there are two key questions that we were thought about over the last few years. For question A is, how do we identify flavor instabilities in the simulations? Okay, and question B is how to approximate the fate of neutrino flavor conversions in the nonlinear region. All right, so yeah, before we just mentioned linear region. Okay, So there were like four different works working on that over the past few years. Yeah, so two of them, including me, as shown here. We basically took the strategy that we just post-process simulation data. So by doing that, say we ask for simulation outputs from hydrodynamic simulators who do not include neutrino flavor oscillations, and then we define what are the neutrino emission surface, and then we parameterize the neutrino emission angular distribution at their respective emission surface. And then we ray trace those neutrinos to obtain full angular distribution everywhere above the surface. Okay, so we do that for two different cases, one for black hole accretion disk system in 2017, another one for early post-merger cases in 2020, last year. Okay, and the other way that one can do that was just done very recently this year is people try to look for instability, not fully deriving using the full angular distribution of neutrinos, but just looking in particular for some instability corresponding to some particular K mode. Okay, and in this way, people can develop a way that basically, yeah, if you just do say the N1 moment transport, then you can actually using the moments to simply calculate the flavor instability corresponding to, for example, K equals to 0 mode, the homogeneous mode. Okay, so it was this kind of identifying the ability of identifying instabilities, then one can actually couple the flavor instability, identify flavor instability while running simulations. I call it in situ simulations. Okay, so one very recent paper by Lee and Siegel just a few months ago, they did it for black hole accretion disk system, and then we also worked together with Oliver Eust and Sajay Abbar to also look at the similar black hole accretion disk system. So that is, yeah, I will, those are basically the way that we identify instability now. And the next one is how to approximate those fate of oscillations, right? Okay, so there are also two different ways of treatments in literatures, in those literatures, okay? So the first one that we initially adopted and also follow, also adopted by Lee and Siegel was that we assume the full flavor equipartitions separately for neutrino sector and for anti-neutrino sector. So basically what it means that if you identify and flavor instability, then you assume that immediately from that local point, you have your neutrinos are neutrino sectors for neutrino with different flavors in neutrino sectors are all having equal number of, say, distribution function, and likewise for anti-neutrinos. Okay, and in our work like this in preparation, we try to also use a different methodology to say approximate the fate of flavor conversion in nonlinear regime. I call it now a partial flavor equipartition, which can serve the net E minus mu neutrino lepton number. I will talk about that more later. Okay, so then after specifying all the terminologies, then let's look at what we obtained in all those different works. Okay, so the first one that we did back in 2017, again, was we used post-processing, full flavor equipartition, and look at the black hole accretion disk wind only. Okay, so the simulation was taken from Oliver in 2015. Okay, so from there, basically there are three snapshots shown here that are taken at different time in Oliver's simulation. And just like you saw before, wherever we see a colored region, that means that we identify flavor instabilities. Okay, so we can see that over the evolution of several tenths of milliseconds, the majority part above the neutrino emission surface shown by the red and the blue line here are unstable to, yeah, in the neutrino flavor sector. Okay, so if we then enforce the full flavor equipartition and then run the nuclear reaction network to compute how the YE would change for cases with and without flavor equipartition. And what we found is that, for example, for the case of no flavor equipartition, then initially those YEs are very high, say ranging between 0.35 to 0.5, can be reduced to centered around 0.25 when you force flavor equipartition for the neutrino sector. Okay, so why is that so? That is basically because the oscillations here, because in this neutrino, the black hole accretion disk system do not emit much new X. So what oscillation does is basically it leads to smaller neutrino fluxes above the neutrino emission surface, and therefore they lower the neutrino absorption rate. That means that you have lower YE and you have more heavy elements. Okay, so that was the story at 2017. All right. So the next case that we examined was the simulation done by Galactic group, for which they basically do we look at the roughly 10 millisecond window post a neutron star, two neutron star merges. Okay, so once again, you see all the colorful regions above the neutrino emission surface, and that means that we identify again all the flavor, all regions are unstable. Okay, in flavor sector. Okay, and interestingly, in this particular case, we find a different effect when compared to what you saw previously. Okay, for example, if we look at now the polar ejecta, when we also assume full flavor equipartition and then do the nucleosynthesis computation, and for polar ejecta now that is confined within say 30 degrees away from the z-axis, then what we found is that now the flavor oscillation actually helps, or flavor equipartition actually helps to increase the YE in the polar region. Okay, and you may want to ask why. Okay, so the primary reason is that here, because in those early post-merger cases, if you remember the very first slide, we also have a lot of new X. Okay, so your flavor oscillation actually leads to a higher, a relatively larger ratio between the number of electron neutrino flux versus that of electron antineutrinos. Okay, so this then leads to a higher YE for the region of ejecta that exposed to larger neutrino flux. So the result is then that in those polar ejecta, then you actually enhance more iron peak nuclei and then lower the first peak nuclei when you include the flavor equipartition. Okay, so I must mention the work done by Lee and Siegel because that's a very nice work. Okay, so what they did this year is that they put this in situ formalism, the way that they can include neutrino equipartition in situ in simulations. Okay, so using the method that we described before. Okay, so they do it for, after they identify a flavor instability, they again assume flavor equipartition, full flavor equipartition, and they run it for black hole accretion disk system with MHD. Okay, so what they found is that okay, so this once again shows that they identify almost everywhere in the disk. Even inside the accretion disk, there are flavor instabilities, as shown by the colored part in the lower panel here. Okay, so what they found is that, in this case, the neutrino flavor conversion, taking into account flow flavor equipartition, can once again lower the YE from this green to the yellowish histogram. Okay, and that can somewhat change, for example, the length-time mass fraction, length-time number fraction, or the third peak height by a factor of few up to a factor of 10-ish in this simulation. Okay, and yeah, this is somewhat different from what we found a few slides ago, because there we only look at the neutrino-driven wind, and then here they look at all the early disk ejecta from the MHD simulation. And so, in fact, I would say that I found even larger effect on the disk ejecta compared to what we found before with post-processing. Okay, so then the last slide that I want to show here is that before going to the conclusion is that we also are now doing the similar in situ simulations actually before they publish their paper. And what we do differently is that we assume now a partial flavor equipartition. Okay, so why is that? Okay, and this is because if you, I don't have time to talk about that, sorry, but if you look at the full equation of motions, then you find that if you only include the fast flavor neutrino oscillation terms, or let's say the neutrino oscillation Hamiltonians, then the equation of motion requires a net E minus nu lepton number as conservation. Okay, so that means that if you start with a bit more electron antineutrino and a bit less electron neutrinos, okay, then when you convert your electron neutrinos, when you redistribute your electron antineutrino and the electron neutrino away, then you must conserve the net electron neutrino lepton numbers. So you cannot actually, if everything is dictated by the phase of flavor oscillation only, then you actually cannot assume full flavor equipartition. Okay, so what we do is then we only get either neutrino antineutrino gets flavor equipartition. And then for the other one, we redistribute exactly the same amount among another sector. Okay. So then we Oliver run a simulation for 3 solar mass black hole plus 0.1 solar mass accretion disk, similar to what Lee and Siegel did. And what we found as a preliminary result is that the effect of flavor oscillation here actually gets much reduced. Okay, so we are still trying to look at why this is so, and whether there's some, for example, angular dependence, etc. Okay, so yeah, that's basically my talk, the main content. So the take-home message is that, okay, several studies, as I mentioned, have shown that the neutrino flavor oscillations can potentially affect nucleosynthesis in outflow from merger remnants. However, there are several key improvements that still need to be made in order for us to reach a robust conclusion. Okay, so for example, we may need a more complete case study. So far the studies are confined to black hole accretion disk system and the early post-merger remnant, and there's no analysis being done for, say, long-term hypermassive neutron star accretion disk case yet. Okay, and we now can only use parameterized method to approximate the nonlinear outcome of flavor oscillations. And those are basically like guided by some principles, but still sort of ad hoc. So we probably need to further develop multi-dimensional neutrino flavor local simulation for neutrino oscillations, and then see if those simulations, local simulations, can provide further guidance. Okay, and there are also some curious aspect that was recently discussed. I particularly highlight those two by Lucas Jones and Rogero in this year. So with that, I thank you for your attention.
Okay, thank you so much, Mengru. We're now open for questions, and we have a first question in the chat from Gail. And she asks, do all your calculations assume k equals 0? Typically, how different is the growth rate of the instability at k equals 0 compared with the maximum growth rate?
Okay, yeah, very good question. Okay, so for example, for those post-processing work, for plots that we show here, they are all corresponding to k just equals to 0. Okay, but in fact, we analyze the full dispersion relation, and for non-zero k, the imaginary omega that corresponds to non-zero k mode, they usually are in similar orders of magnitude, but can be larger or smaller by a factor of a few. Okay, but for the simulation purpose, probably doesn't really matter that much if we just want to do it, because as you see that the length scale is much shorter than any other scale in the game. Okay, well, in the case of Siegel et al., they only strictly only identify instability corresponding to k equals to 0 mode. Okay.
Thank you.
Okay, thanks. Any other questions? We have time for maybe one more quick question. Well, if I could ask one, your outcome of the nucleosynthesis seems to be really sensitive on the amount of mu and tau neutrino emission, yes? And how certain is this, and what disk parameters go into the amount of mu tau emission that you see?
Okay, yeah, okay. Good but difficult question. Okay, right. So as we know that I believe that we all know the merger, the neutrino transport in mergers are not as good as the neutrino transport in supernovae, right? So for example, in the very first plot, yeah. So those in the simulation done by Gahin group, for the nu and tau sector, the included reactions are much less. For example, there are basically no the nu and tau scattering of electrons. Okay, so for example, that is why you see these average energies are so high. Okay, compared to other flavors. And then we all know we knew that from supernova, right? If you include that, this will go down by some drop to probably to 20 or below 20. Okay. So when we post-process the nucleosynthesis, we actually try to take that into account. So we borrow what we learned from supernova and effectively lower the mu and tau mean energies when we post-process. But of course, as you said, there are still uncertainties, and I don't think it is very easy to quantify now.
Okay, great, thank you.
Thanks.
Okay, so thanks again for this nice talk and discussion. I
Thank
think
you.
we will move on to our next talk. Abhishek Das will tell us about prompt collapse. Great, I see you
Hi,
there. Hello, how are you?
I'm good. I hope everyone else is doing well too. So I will share my screen now.
Please go ahead.
Okay.
All right, so take it over. I will give you a 2-minute warning.
Thank you so much. So first of all, I want to begin by thanking the organizers for giving me this wonderful opportunity. So I am a graduate student in the group of Professor David Radici at the Pennsylvania State University. And today I'm going to talk about prompt collapse in binary neutron star mergers. So, I'll start by just showing the various possible outcomes of a binary neutron star merger process. And I'm sure that everyone in this meeting is familiar with all of these outcomes. But the major branch that happens, like as you can see, there are multiple different stages that are there in this process of binary neutron star mergers, but the major branching happens just at the stage of the merger where you can either have a black hole formation immediately upon merger, which is what we call prompt collapse, or you can have a short-lived stable remnant, which then emits angular momentum in the, loses angular momentum by emitting GWs. And in that process, ends up either settling down as a stable neutron star or later collapses to a black hole. So in this study, we will focus solely on this particular branch and ignore all of these possibilities. So let me give a brief introduction to the work that has already been done in this field and what is the current state of the art. So the first paper that I found on this is by Hotokezaka et al. From 2011. And they first classified binary neutron star mergers on the basis of these two outcomes, namely a hypermassive neutron star or a prompt collapse. And they made this classification on the basis of whether the core bounces upon merger or whether it collapses steadily to a black hole. And this is the condition that we use as well in our study. And they also identified that there is a critical mass for every equation of state, exceeding which a binary neutron star would always undergo prompt collapse. And the graph that they presented here shows the differences in the behavior of the maximum density or the central density for different outcomes. And you can see here that for a prompt collapse case, the density rises very sharply upon merger. Whereas for a delayed collapse case where we have a stable neutron star for some time or a differentially rotating neutron star for some time, we see the maximum density rising more gradually. So the next work in this topic is by Bauswein et al. From 2013. And they were the first to give us a correlation between the ratio of the threshold mass and the maximum allowed mass for a given EOS and the compactness of the maximum mass neutron star for the same EOS. And they found a good linear correlation for these two quantities. So the next work in the field is also by Bauswein et al. This is a paper from 2017. And here they take their observations one step further and use the correlation derived in the previous paper to find a radius constraint for neutron stars from the observation of GW 170817. So we know from the amount of electromagnetic counterparts that we got from GW 170817 that this is almost impossible to be a prompt collapse situation, and it is very likely to be it is very likely that there was a neutron star remnant for some time at least. So we can treat the total mass of the GW170817 binary to be a lower bound for the threshold mass for prompt collapse. And there is another constraint that has been implemented in this graph, which comes from causality. So only the blue shaded region in this graph is permitted to be populated by neutron stars. The white region is excluded because a neutron star lying in the white region would essentially have a sound speed which is greater than the speed of light, and that will violate causality. And the black curves in this graph are basically lines of constant radius, which are derived by taking the equation for the linear correlation between K threshold and Cmax from the previous paper. So that would be an equation of the form K threshold equal to A times Cmax plus B, where A and B are the slope and intercept respectively. And there, if you substitute the expressions for K and Cmax in terms of Mmax and Rmax, and if you simplify that expression, then you see that we'll get a quadratic equation for M threshold in terms of Mmax for a constant value of Rmax. And this is what these lines are. And by plotting like several of these lines, we see that the lowest value of Rmax, which intersects the allowed region of parameter space, is Rmax equal to 9.26 kilometers. So this provides a lower bound for Rmax in a neutron star. And the next paper that, the next paper that I looked at was by Coppel et al. From 2019. And they were the first to propose a nonlinear correlation between K threshold and Cmax. And they argued that this kind of a correlation would provide the limit for the black hole, which is essentially that the ratio of M threshold by Mmax should go to 0 for Cmax going to half. And they also use their relation to update the radius constraints from the previous paper by Bauswein et al. And they obtained a tighter correlation for the lower bound of Rmax. And last but not the least, I'd like to show this paper by Bauswein et al. From 2020. And here they show something really interesting. So this is a plot between the combined tidal deformability for the threshold mass case and the mass of the threshold mass case of the for a particular equation of state. And here they show, or rather they present that this dashed black line separates the parameter space into two different regions. And the lower region is allowed to be populated by both hadronic as well as hybrid equations of state. And by hybrid equations of state, I mean an equation of state which can undergo a phase transition to pure quark matter within the core of the neutron star. And they argue that the bottom region can accommodate both hadronic and hybrid equations of state, whereas the top region can only accommodate hybrid equations of state. The reason for this is that this phase transition essentially softens the equation of state further, and therefore this particular region of parameter space should only be accessible to those neutron stars which have been softened by a phase transition in their core to pure quark matter. And later in the talk, I will show some of our results for the different results that I showed from previous works in literature. So this is essentially the entire set of equations of state that we have used in our simulations. As you can see, it's a large number of equations of state. And the black dots on the graph are represent the binaries that we have simulated. And I should mention here that we have simulated only equal mass binaries. So these are all the binaries that we have simulated, and the red dots represent the threshold cases. So essentially the lowest mass binary, which demonstrates prompt collapse for each equation of state. And the way we found the threshold mass for prompt collapse was by a method of intersection. So we essentially started with the two most extreme masses on this graph, and then we essentially so we started with the two most extreme masses and the mass that lies in between these two. And we saw that we saw what the outcomes for each of them are. And then we took the two which showed two different results, which is the lowest mass prompt collapse and the highest mass a massive neutron star remnant. And then we simulated the one in between and saw the outcome for that. And in doing so, we were able to find the threshold mass for prompt collapse for each of these with error bars of 0.05 solar mass each. And the code that we used for our simulations is Whiskey THC. And this is the code paper for the code that you can refer to for more details. But in short, it solves the BSS NOK equations, and it has a second order convergence for GR hydrodynamics, and it conserves the lepton and baryon numbers and also energy and momentum. For neutrino transport, it has a M0 scheme, which as one of the previous speakers described, is a leakage scheme. And it is an approximation, but it is good for our particular situation because the phenomenon that we are studying is of the order of 1 millisecond, whereas neutrino cooling phenomenon timescales are of the order of seconds. And finally, our code can accept both tabulated and piecewise polytropic equations of state. So I want to show some of our outputs from the code and describe briefly how we identify prompt collapse. So as I mentioned earlier, we use the criteria of core bounds to determine whether a binary neutron star underwent prompt collapse or had a stable remnant. So in this case, the first column shows the minimum lapse function, the density, the central density, and the L equal to 2, M equal to 2 mode strain for a case that was not a prompt collapse. So this had a very long-lived remnant, which survived for the entire length of the simulation. And as you can see here, the core bounces multiple times. So the minimum lapse function is an indication of the lapse function at the center of the star near the core. So the bouncing of the oscillations in the minimum lapse function indicate that the core underwent multiple bounces after the merger process. And similarly, you can see the density also, instead of rising sharply, it oscillated multiple times before plateauing at the maximum value. And from the strain, you can see that there is, so this is roughly where the merger took place. So you can see that there is a large part of the signal that also is obtained after the merger. So this is a case. The second column is a case which also had a massive neutron star outcome, but the massive neutron star collapsed almost immediately to a black hole. So you can see from the minimum lapse function that it only underwent one core bounce, and then it collapsed promptly to a black hole. But since it had at least one core bounce, we will classify this as a massive neutron star outcome. And similarly for the density, you can see that it had a couple of oscillations and then quickly rose to the highest value for corresponding to a black hole. And for the strain, you can see that there is not a significant portion of the strain after the merger. And finally, the third column is a case of prompt collapse. Here you can see that there is no bounce in the core. It quickly falls to nearly a zero value. The only deviation is this tiny spike here, which is due to the formation of apparent horizon. So when an apparent horizon is formed, the tracker for the minimum lapse essentially suddenly jumps from the center of the star to the position of the apparent horizon. And that is why you see this jump. This is not a core bounce. And similar to what Hotokezaka et al. Had said, we see that the density rises quite sharply and reaches the maximum value promptly in the case of prompt collapse. And also in the strain, we don't have anything after the merger. So this is another thing that I wanted to show, that one way of identifying whether a binary neutron star underwent prompt collapse or not is to look at the amount of ejecta. And here the red curves correspond to ejecta from prompt collapse cases, and the blue ones correspond to ejecta from massive neutron star cases. And we can see that for most of the cases, the ejecta from prompt collapse is orders of magnitude smaller than the ejecta from massive neutron star outcomes. Please note that this is the y-axis is in log scale. So in most cases, this is at least one order of magnitude smaller, and this indicates that for a prompt collapse, there is not much ejecta because most of the ejecta falls back into the black hole. And now I will show you a little movie that I made to demonstrate the dynamics of a prompt collapse case. So this is the in-spiral stage, and then you can see the stars touch briefly. And here you see something interesting. So this is essentially the formation of the apparent horizon. Although I should give a disclaimer here that this is not the actual apparent horizon, because our apparent horizon code failed to find the actual apparent horizon, which I believe is due to the parameters for the search not being calibrated properly. So instead, what I'm showing here is an approximation of the apparent horizon, which is plotted using a contour of lapse equal to 0.3, which is a conservative approximation, because in all the cases that we looked for prompt collapse and also massive neutron stars, we saw that for most of the cases where the minimum lapse goes below 0.3, it does not recover and undergo a bounce. Rather, immediately it collapses to a black hole. So here you can see the apparent horizon forming, and slowly the black hole essentially sucks most of the matter back into itself, which is shown by the diminishing of the red region, which is the contour for 10 to the power 13 gram per cc. And there is, of course, still some matter which is ejected, but it is much less compared to what we would get in case of a neutron star merger remnant. Okay, so let me now go to the next slide. Okay, so now I'll just show our results for our study. So the red line here corresponds to our fit of K threshold versus Cmax. And here we have also combined our fit with the data. We have also considered the data from Hotokezaka et al. 2011 for making this fit. The reason is that they have also used a code which is very similar to ours, namely a fully relativistic code. And we see that including their data does not give a significant deviation for our fit parameters. And in green, we have represented the fit from Bauswein et al. 2013. And we see that while it has a has quite a good agreement in the slope. There is a deviation in the intercept. And one possible reason for this could be that the code that they used for their simulations was a conformally flat code. And this is one result that we observed for the first time, like it has not been reported in literature before, is a correlation, a good correlation between the quantity C threshold and M max. And this is particularly interesting because we can study this relation further, and it can give us a critical collapse condition for prompt collapse. This is something we are still investigating. And here I have demonstrated the radius constraint, which Bauswein et al. Showed in the 2017 paper. We have updated it for our work, and we get a lower bound for Rmax as 9.80 kilometers, which is a tighter bound than both Bauswein et al. 2017 as well as Koppel et al. 2019. And finally, this is a plot between three different quantities, namely lambda 1.4, which is the tidal deformability of the 1.4 solar mass neutron star, M max and M threshold. And the purpose of this graph is to basically explore some more constraints on the parameter space. And as you can see, we can already use this kind of graphs to eliminate certain equations of state. So here, this particular equation of state, which lies in the gray shaded region, is already excluded from the constraint coming from M max. So this is a constraint on M max coming from pulsar observations. So we know from pulsar observations that the maximum mass neutron star has to be more than 2.01 solar mass. And last but not the least, this is our version of the plot for lambda threshold versus M threshold, which was explored in Bauswein's 2020 paper to segregate the parameter space into a hybrid only region and a hybrid plus non-hybrid equation of state region. And this is a counterexample because the only equation of state from our study, which happens to lie completely in this region, that is not even having error bars intersecting with the mixed region, is actually not a hybrid equation of state. So this essentially indicates that we should look further into the numerical numerical calculations that went into computing this line of segregation. And that's all I have for today. Thank you very much. And I will now accept questions.
Thanks for this nice talk. Are there any, we have a couple of minutes for some quick questions, if there are any immediately.
Okay, great. I just wonder if you could maybe elaborate more on your last plot. So do you know the differences that lead to this observation that you have a non-hybrid AOS that is above the line from Andy Bauswein et al.?
Right. So the argument that they presented in the paper is that this region of parameter space can only be populated by neutron stars which have undergone a phase transition to pure quark matter in their core, because it is otherwise not likely that, or not possible that a neutron star with threshold masses this low will have a high value of such a high value of lambda. And this is because the hybridization or the phase transition in the core essentially makes the equation of state softer, which enables it to have a higher tidal deformability. But I am not aware of the specifics of the calculation that went into deriving this particular line here. So this is something we would like to investigate, because this equation of state which we found that lies in this particular region is clearly not a hybrid equation of state. It is a tabulated equation of state with nuclear physics parameters, but it has no provision to undergo a phase transition to quark matter. So this warrants further investigation. Does that answer your question?
Yeah, maybe can you also tell me which equation of state that is above?
So this is not an equation of state that is public yet. This was provided to us for exclusively for our study. But we are going to publish this work soon. And once we do so, we will also release our data publicly on Zenodo. So then you will have the opportunity to look at this for yourself.
Okay, great. Thank you.
You're welcome.
Okay, thanks again. And I think it's time we need to move on to our last talk. So
thank you very much.
Yeah, thank you. Oleg. So our last talk is Oleg Korobkin, who will talk about multi-D aspects of kilonovae. Oleg, are you there? Can you unmute yourself?
Yes, can you see my screen?
Yes, we can see. Yes, I can see your screen. Great. Okay, welcome, Oleg, and
right, wonderful.
take it away.
All right, thank you for giving me the opportunity to speak here. So I will be talking about multidimensional aspects of kilonovae. So this is a work that has been done in large collaboration at LANL with Ryan Mulliger, Grace Fryer, and other people here. So this is the picture that we all have of our process in neutron star mergers and black hole neutron star mergers. So it's quite familiar. So you have a dynamical ejecta, which is shown in red here. It doesn't necessarily mean that it's always producing the red kilonovae. So you could have cases where it produces blue kilonovae and vice versa. And so this is just a kind of a schematic description. So you have neutron star mergers that produces a hypermassive neutron star, or which subsequently collapses to a black hole, or does not collapse to a black hole and generates a strong wind. Then you have a wind from the accretion disk, and you have a variety of different ejection channels. So the main takeaway from this picture is that the kilonovae are highly asymmetric objects. They're not spherically symmetric. And as Stefan mentioned earlier today, it may be tempting to start estimating the masses of ejecta from simple analytic formulae, but as I will show here, this can lead to wrong results. And multidimensional models of kilonovae produce a wide diversity of different transients. So our main tool for investigating multidimensional nature of kilonovae is the SuperNu. It's a multidimensional Monte Carlo radiative transfer code developed by Ryan Walliger and Van Rossum. It's an open source code. Several groups are already using it. So by saying multidimensional here, I will only be talking about axisymmetric kilonovae, but the code also works in 3D. It combines implicit Monte Carlo scheme with discrete diffusion Monte Carlo in the optically thick regime. It accurately calculates the thermodynamic conditions in the underlying background flow, which is a partially ionized multi-component plasma. It assumes strictly homologous flow, and it's a first order. It includes relativistic corrections up to first order. So the opacity is taken from detailed atomic opacity calculations that are provided in the tables with, well, in this particular simulation, 1024 log-spaced wavelength bins. that span wavelengths from 10 nanometers to 12.8 micrometers. So the questions that we want to address when we're talking about multidimensional pictures of kilonovae is, what are the uncertainties? What can and cannot be inferred about ejecta geometry from kilonova spectra and light curves? How large are the uncertainties that can be produced by simply varying where the mass is located in the velocity space? And well, can we answer unambiguously the question of what's the composition of the ejecta? And can we ultimately do some kind of a kilonova tomography where we look at the spectra and the evolution of the spectra and reconstruct the three-dimensional picture? And ultimately, we want to, of course, answer the question of the origin of our process and the high-density equation of state. So as I mentioned before, the ejecta has a highly non-spherical character. For instance, dynamical ejecta most likely has this toroidal shape as shown on the left, and the wind has is more of a poloidal outflow. So unlike supernovae, in which things are more spherical, this has to be considered. And it's also multi-component. So you have a red lanthanide-rich ejecta, and you have a presumably blue lanthanide-poor ejecta. But it can be different, and some simulations show that this can produce lanthanide-rich ejecta, and some of the dynamical ejecta can be also lanthanide-poor. So in order to be kind of agnostic to this possibilities, we try to model them with different combinations. So in this study, we use two different components where we just prescribe certain opacities certain compositions which impose the opacity and the nuclear heating corresponding to nucleosynthesis models. So here we use, so these are the opacities, this is the compositions that we use for the blue and red components. And then in order to investigate, to kind of provide a model-independent view, we construct different potential morphologies, like hourglass morphology or toroidal morphology, spherical morphology, and we combine the red and blue components and just look at the different light curves produced by these combinations. And so it turns out that this morphological variability just in the bolometric light curves leads to a large diversity in the peak times and peak luminosities. So here you can see that bolometric luminosity, just simply by rearranging the material in a different morphological sense, can shift the peak by 2 orders of magnitude and can shift the peak time from 0.25 days to up to 8 days. And so it's also important here that this effect is particularly pronounced for detailed temperature-dependent opacities. So what this means is that without strong constraints on the geometry that could be provided by simulations, artificially large or small masses can be inferred from non-spherical explosions. So these models also allow us to investigate different multi-component interactions between different types of ejecta. So here are the different effects that you could expect. So one, which was discovered 2015, is the lanthanide curtain, is the the case where the blue emission is obscured by a very opaque lanthanide region. Then you have a case of a flux reprocessing, where you have two components, and the heat generated by radioactivity, for instance, in the blue component, travels to the red component and gets re-emitted there. And you have double reprocessing, where, say, it's the photons can be scattered several times between different components, and we saw evidence of that as well. Well, another kind of a more simple effect that you can see and you can expect from multidimensional nature is the effect of the projected area of the photosphere. So this effect basically varies the light curve within a factor of a few. So maybe a factor of 2. But other effects can really dramatically alter the spectra. The most interesting effect is this number 6, which is the heat retention. So if you take the material and instead of, if you take the material in the ejecta and distribute it in a different way, it can, so you change the density, and correspondingly you can also change the temperature in the ejecta. So if you have the same mass and the same average expansion velocity, you can still redistribute material. For instance, instead of having one spherical expansion, you distribute it into 2 dense clumps with the same mass and the same expansion velocity. You can get higher temperature at late times, and correspondingly different luminosity, different brightness, and different spectra. Finally, you can also have, obviously, pi Cygni features from individual lines. So here is an example of 2 different effects in the spectra that we calculated for a model that has a toroidal toroidal lanthanide rich ejecta and a spherical lanthanide poor ejecta, kind of a blue component, which is displayed by this cartoon here. So if you look at this configuration from the edge, the red ejecta obscures the blue one, and you see significant drop in the optical emission, which is shown by the difference in green and blue edges of the spectra in the blue region, in the optical region. You also see effects of a double reprocessing here. So the black line here corresponds to just the spherical component without toroidal component. So you can see that it lies in the middle for the optical emission between the on-axis and equatorial view, which means that effectively this toroidal dynamical ejecta acts to reprocess the light from the blue ejecta and redirect it towards the poles. This is an example of pi Cygni features from neodymium opacity lines. Obviously, it has to be corrected for non-LTE effects, but this is a very interesting effect. It manifests itself when you have a slowly expanding torus. So if the expansion is sufficiently fast, it's smeared out, and you don't see these lines. So anyway, in the coming to the conclusions, we can say that without strong constraints on geometry, you can easily infer, you can easily be off by an order of magnitude about the mass of the ejecta. Heat retention in models with local density enhancements produces long-lasting bluer kilonovae. as a tiny mass of lanthanide-rich component is enough to fully block the optical emission of a blue kilonova, which was already discovered and shown in 2015 in papers by Kaysen. At late epochs, at about 1/8 days, models with rapidly expanding lanthanide-rich ejecta exhibit pronounced pi-Cygni features, allowing the characterization of composition and line of sight velocity of the ejecta. And finally, double reprocessing and flux focusing by toroidal component can increase kilonova brightness in addition to the projected area effect. Yeah, that will be all for me. Thank you very much. Questions?
Okay, thanks so much, Oleg. Any questions or comments? Go ahead and unmute or answer them in the chat. So I can start things off with a question I had. So you say without constraints on geometry, how could we get constraints on the geometry? Do we have to rely on simulation, or are there observational characteristics that we can look for, like the, I guess, the line widths that you mentioned, but are there others?
Well, I guess we have to rely on the simulations in the end of the day. But like when, as you can see here, there is obviously an effect of the line widths. You need a very complex kind of integrated approach to the picture, and otherwise you can infer pretty much anything from these events.
Right, and these are just the uncertainties from the morphology that you're discussing, and there's a whole additional uncertainty due to the nuclear physics that I'm sure we'll talk about more as the week goes on, which it just increased that uncertainty even further. Okay. Any other final comments or questions for Oleg? Well, I want to thank all of the speakers today for their very nice talks. This is a great first day of the workshop. We're going to start off our program tomorrow with a discussion section. So I encourage you to think about these talks and about the questions raised. And we will, again, start the discussion tomorrow first thing. With that conversation, and I hope to see you all there and look forward to the talks tomorrow. So thank you, everyone, and I will see you tomorrow.